Hello there, and welcome to another quiet night with the Sleepless Scientist. Tonight we'll wander into a story that begins with the sun, that bright companion that has risen over every human who has ever lived, and whose light has been woven into our myths, our rituals, and our science. If you enjoy this quiet wandering, a like or subscribe would mean a lot. Share where and what time it is. It feels like gathering around one fire across the world. Now, soften the room, let a hum keep you company, and let's begin. And if you drift off, that's more than fine. The story will keep unfolding, whether your eyes are open or closed. The sun has always been more than just a star in the sky. For ancient cultures, it was a god, a ruler, a witness to every field and every prayer. In Egypt, it was Ra, the falcon-headed deity who rode a fiery barge across the heavens each day, only to descend into the underworld at night to battle serpents before rising again. In Greece, it was Helios, steering a golden chariot drawn by horses whose hooves struck sparks across the dome of the world. In India, it was Surya, the radiant one with 7 horses pulling a celestial carriage, each horse a ray of light. To live beneath the sun was to live beneath something alive, something watching, something that granted crops and withheld them, that painted the seasons and marked the rhythm of life. To those early eyes, it was not just a glowing ball of fire, but a heartbeat outside ourselves. It is worth pausing here, letting your mind settle on the image of a sunrise. Imagine standing on a hill while the horizon glows faintly red. The air still cool, birds barely stirring. The first line of gold spills over the edge of the world, and the sun rises slowly, like a great lantern being lifted to brighten the day. It feels timeless, inevitable, and yet each sunrise is fresh, unique, and personal. This is the rhythm that carried our ancestors from one generation to the next. They did not need equations to know the sun's power. They felt it in their skin and bones, in the warmth after winter, in the lengthening shadows of autumn, in the seed that sprouted only when light returned. But curiosity never sleeps, not even in those ancient days. Slowly people began to ask, what is the sun really? If it is a god, why does it rise so precisely, always keeping its time? If it is fire, why does it never burn out? A campfire, after all, lasts only a few hours before the logs are reduced to glowing ash. A lantern sputters out when its oil is gone, but the sun had been burning for as long as anyone could remember, for countless lifetimes, and its flame never seemed to dim. The question lingered in the background of history. What is this endless fire? At first, the guesses were poetic. Some thought it was a flame fed by divine breath, as if each dawn were a god's exhalation. Others imagined it as a great coal burning in the sky, tended by unseen hands. Even into the early days of science, scholars believed the sun might be like an enormous furnace, burning some material, wood, oil, or coal-like matter, until it ran out. It was not a foolish guess. If you'd only seen fire on Earth, you would imagine fire in the sky must be similar, only larger. Yet the more people thought about it, the less it added up. If the sun were burning like wood, it would have exhausted itself in just a few thousand years, and the Earth would already be dark. Clearly something else was at work. From here begins the long journey from myth to science, from reverence to reasoning. The sun went from being a personality in the heavens to a puzzle waiting to be solved. But even as science advanced, the old myths never entirely faded. They softened into metaphors, into art and poetry, reminding us that knowledge and wonder need not exclude one another. When you see the sun as hydrogen fusing into helium, it is not less majestic than Ra's journey or Helios's chariot. It is simply another story layered atop the old ones, another language to describe the same awe. And in truth, the scientific story is no less grand. We now know that the sun is a star, one of billions, born from the dust of earlier stars. It is not burning wood or coal, but weaving atoms together turning light hydrogen into heavier helium, releasing vast amounts of energy in the process. The sunlight you feel on your face when you step outdoors is the final step in a chain that began in the very core of the sun, where pressure and temperature rise to levels unimaginable on Earth. It takes photons, tiny packets of light, thousands of years to escape from the dense interior to the surface, bouncing, scattering like restless children in a crowded room. And yet, when they finally emerge, they race across the 93 million miles to Earth in just 8 minutes, lighting the morning as if it were effortless. The sun's story is thus both ancient and ongoing. It was born 4.6 billion years ago from a cloud of gas and dust, the remnants of stars that lived and died before it. When those earlier stars ended in explosions, supernovae, they cast out heavy elements, iron and gold and carbon, seeding the cloud that later collapsed to form our sun and its planets. You and I carry atoms forged in those earlier fires. Every breath, every heartbeat, is a continuation of that stellar lineage. In this sense, the myths were not entirely wrong. The sun is divine not because it sits on a throne, but because its light carries the story of countless generations of stars. It is a torch passed down, not a solitary flame. So tonight, as we begin our journey into the origins of the universe's simplest ingredients, hydrogen, helium, and the elusive lithium, it is fitting to start with the sun. It is both our local furnace and a reminder of cosmic processes that span billions of years. It links the myths of our ancestors with the equations of our scientists, and it offers us warmth in the morning and direction in the night sky. The sun is not just the nearest star, it is the most personal. It shapes our calendars, nourishes our crops, and has guided us from stories to science. And in that glow, we see the first hints of how the universe itself emerged from chaos into order, from fire into form. For much of human history, the sun was not something to measure, but something to live with, a faithful presence overhead that gave light for crops and warmth for skin. Yet at some point, the sun became not only a companion in the sky, but also a puzzle. It was a flame that never seemed to die down, a fire that had burned since the beginning of memory. That very constancy was what made it so mysterious. A campfire needed fuel, a lantern required oil, even a candle would surrender in just a few hours. Yet the sun gave no sign of exhaustion. It rose every morning, its light undimmed by centuries, its warmth never faltering even across the rise and fall of civilizations. People began to ask, quietly at first, but more insistently as time went on, what kind of fire could last forever? The earliest attempts to explain the sun's power were imaginative and surprisingly practical at the same time. In the 17th and 18th centuries, as science gained momentum, scholars suggested that the sun might be a ball of burning coal or some similar material. It was not a foolish idea. Fire was the only reference they had, and coal was known to burn hotter and longer than wood. If the sun were truly gigantic, perhaps its supply of coal was vast enough to last for thousands of years. The problem with this picture, however, is that the math refused to cooperate. A sphere of coal the size of the sun would indeed shine brilliantly, but not for billions of years, more like a few thousand at best. To anyone who believed the Earth to be ancient, or who saw the fossil record stretching back through unimaginable spans of time, the coal theory simply did not last. The sun, by that logic, should have already burned itself into darkness. Later theories were more sophisticated but still fell short. Some thinkers imagined that the sun's heat came from gravitational contraction. As a massive cloud of gas collapsed inward under its own weight, it could convert potential energy into heat, radiating light in the process. The 19th century scientists Hermann von Helmholtz and Lord Kelvin promoted this idea, suggesting that the sun was slowly shrinking and that the pressure of its own collapse provided the energy we see. This too had an elegant logic. Compressing a gas does produce heat. You can feel this on a bicycle pump as it warms in your hand. Yet calculations showed that such a process would only allow the sun to shine for about 20 million years, far too short compared with the geological evidence already recognised on Earth. Once again, the numbers betrayed the idea. The sun simply endured too long for these explanations to hold. Imagine for a moment the frustration of those scientists. They could measure planetary motions with exquisite precision, calculate tides and eclipses, predict the swing of a pendulum to the second, and yet, when faced with the most obvious, most daily phenomenon, the shining of the sun, they had no satisfying answer. It is, as if you could explain the delicate mechanics of a pocket watch, but not why the hands kept moving. The sun's mystery was a constant embarrassment, a hole in the otherwise growing confidence of science. And still, ordinary people felt the question in their own way. Farmers could not have phrased it in terms of fuel or gravitational collapse, but they knew the sun did not behave like ordinary fire. Children too asked questions that grown-ups could not answer. Why does it never go out? Why does it never shrink? These simple questions were echoes of the same puzzle that troubled the most accomplished scientists of the age. Asking the question was itself a milestone. For many centuries it had been enough to tell stories of Ra or Helios or Surya, to weave the sun into a tapestry of gods and rituals. Those stories gave meaning, but they did not give mechanism. The shift to asking how rather than only why was a quiet revolution. It was the seed of what would become astrophysics, born not from abstract mathematics, but from the wonder of watching dawn and daring to believe that an answer might be found. There is something comforting in realizing that even the greatest minds once stared at the sun with the same confusion we might feel as children. They had the same sensation of awe and the same lack of tools to penetrate its mystery. Galileo could point his telescope at sunspots, carefully sketching their movements, but he could not explain why the surface glowed at all. Newton could describe the laws of gravity that guided planets in their orbits, but when it came to the sun's radiance he was as puzzled as anyone. In those centuries of uncertainty, the sun stood as both guide and riddle. It marked the hours, regulated calendars and inspired poetry, yet it defied explanation. This tension gave it a double role: dependable in practice, elusive in theory. Every dawn reassured humanity that the world would continue, but every dawn also carried the silent question: what is this unending fire? The persistence of that question shaped more than astronomy. It set the stage for deeper inquiry into the nature of matter itself. If the sun's brightness could not be explained by ordinary fire, then perhaps matter held secrets not yet uncovered, sources of energy hidden in the atom's heart. In this way, the sun quietly beckoned us toward the discovery of nuclear physics. The path was long, winding through the laboratories of the 19th century and the insights of the early 20th. But at its root, the motivation was simple. The sun burned too long, too steadily, for any explanation then known. Something entirely new must be at work. Before the age of telescopes that could measure spectra, before detectors could taste the chemistry of starlight, people were left with metaphors. They compared the sun to an eternal flame in a temple, a lamp tended by gods, a coal that never cooled. Each metaphor was wrong in detail but right in spirit. The sun was more than ordinary. It held within it a mystery deeper than imagination. And so we stand, looking back across those centuries, able now to say that the sun shines because atoms fuse together in its core, hydrogen becoming helium, energy released in radiant abundance. But in honouring that truth, it is worth remembering the questions that carried us here. The puzzlement, the failed theories, the childlike wonder, all of it is part of the story. The sun was the first question science could not easily answer, and in chasing its fire we stumbled into the hidden architecture of the universe. If you close your eyes for a moment and imagine the very beginning of everything, you might picture silence, emptiness, perhaps even nothing at all. But the story of our universe begins not in stillness, but in unimaginable chaos. An instant when space itself unfolded, matter and energy pouring outward in every direction. It was a beginning without pattern, without stars, without light, a place where heat and density pressed together so fiercely that no structure could survive. And yet, from that seething origin, a kind of order slowly emerged, like the calm that follows a storm or the settling of flour dust after bread has been kneaded too vigorously. What had been wild and featureless began to cool, to spread, and to organise itself into the building blocks of the cosmos. In those first moments, the universe was hotter than the core of any star, a furnace so extreme that ordinary atoms could not exist. Protons and neutrons, the tiny beads that make up atomic nuclei, rattled around freely, colliding, breaking apart, reassembling, like children playing an endless game of tag. Electrons, those even lighter companions, whirled without belonging to any particular nucleus. It was a soup of particles, restless and thick, a broth with no stable recipe. Only as the universe expanded, stretching out like dough being rolled thinner and thinner across a table, did the temperature begin to fall. Cooling was the key. As the heat faded, protons and neutrons finally had the chance to link arms and stay together, forming the first true nuclei. This moment is sometimes called Big Bang nucleosynthesis, but you might imagine it instead as the universe's first kitchen, a frantic but miraculous attempt at cooking with almost no ingredients. The recipe was astonishingly simple: protons, neutrons, a little time, and an immense oven whose walls were space itself. And from this minimalist pantry came the first great result: hydrogen, the simplest atom, one proton at its core, the original note in the symphony of matter. Alongside it appeared helium, a slightly more complex arrangement of 2 protons and 2 neutrons, balanced and stable, like a pair of dancers holding tightly to one another. And then, in vanishingly small amounts, a more delicate element, lithium, appeared, fragile, fleeting, like a spice sprinkled almost absent-mindedly into a dish and quickly overwhelmed by the stronger flavours around it. It is humbling to realise that nearly everything we see today, every star, every planet, every breath of air and every drop of water, comes from those first simple notes. The universe did not begin with gold or iron, with oxygen or carbon. It began with hydrogen and helium, vast oceans of the simplest elements, and only a faint dusting of lithium. These were the seeds from which everything else would eventually grow. Later generations of stars would forge heavier elements in their fiery hearts and explosive deaths. But in those first minutes, the cosmos settled for simplicity. And it is a simplicity that still echoes today. Look at the composition of the universe, and you'll find that hydrogen remains the dominant element, helium a faithful second, and lithium so scarce that its absence has become one of science's great mysteries. As those nuclei formed, the universe continued to expand. Light, which had been trapped by the density of particles, gradually found room to move. Photons began their long journey, though for hundreds of thousands of years they still bounced from particle to particle, unable to travel freely. Imagine sunlight caught inside a storm cloud, scattering in every direction, unable to escape. That was the universe then, bright on the inside but dark on the outside, light unable to pour forth. It would take time, nearly 400,000 years, for the fog to thin, for electrons to settle into stable orbits around nuclei, for atoms to become whole. Only then could light slip free, filling space with its first true glow. But even before that glow, the seeds of structure were being sown. The early universe was not perfectly smooth. There were tiny ripples in density, tiny clumps slightly richer in matter than their surroundings. These ripples, as faint as the unevenness of a bedsheet pulled too quickly, would one day grow into galaxies and clusters, into the grand tapestry of cosmic webs that span billions of light years. It is strange to think that the stars above your head tonight trace their ancestry to ripples measured in millionths of a degree, imperfections in the baby universe that grew into everything we know. Out of chaos, order, out of noise, pattern. When the first true stars finally ignited, hundreds of millions of years later, they were unlike anything we see today. They were enormous, short-lived, blazing with a ferocity that burned through their fuel in just a few million years. Astronomers call them population 3 stars, but you might think of them as cosmic pioneers, the first to bring true starlight into the dark. Their deaths were equally dramatic, collapsing and exploding, scattering heavy elements into space like sparks from a firework. These ingredients, carbon, oxygen, iron, would later become the soil and air of planets, the bones and breath of living creatures. The universe was teaching itself to cook more elaborate recipes, layering flavour upon flavour, generation after generation. Yet through all these transformations, hydrogen and helium remained the faithful foundation, the bread and butter of the cosmos, and lithium, poor, elusive lithium, remained the odd one out, predicted by theory, glimpsed in trace amounts, but never quite showing up in the expected quantities. Even at the dawn of time, its presence was tentative, as if the universe could not quite decide whether to keep it in the recipe or quietly set it aside. It is easy to forget how fragile these beginnings were. A slightly different ratio of protons to neutrons, a slightly faster or slower expansion, and the universe might have produced a completely different set of ingredients. Without enough hydrogen, stars might never have formed. Without helium, fusion might not have stabilized. And without those stars, there would be no carbon for life, no oxygen for breath, no iron for blood. The calm you feel when looking at the night sky hides just how improbable it all was. The balance had to be just right, and somehow, in those first chaotic minutes, it was. So the next time you step outside on a clear night and see the stars scattered above, remember that what you're really looking at is a story that began in a storm of heat and density, a storm that cooled into the first atoms, the first chemistry, the first glimmers of order in a newborn universe. From chaos came hydrogen, from hydrogen came helium, and with them came the faint, fragile trace of lithium, a reminder that even the universe has its puzzles, its missing pieces, its half-written recipes. And though we now know more than ever about those beginnings, the mystery of why lithium is missing remains, like a soft question whispered across billions of years, waiting for us to listen. If you imagine yourself living a few centuries ago, perhaps in a dim chamber lit only by flickering candles, shelves crowded with glass vessels, copper alembics and handwritten scrolls, you would likely find at least one figure hunched over a furnace, eyes gleaming with the hope of performing a miracle. This was the world of the alchemists, seekers who believed that matter itself could be persuaded, coaxed, or transformed into new forms. Their greatest dream was to take what was common and turn it into what was precious, to transform lead into gold, to move from the dull weight of base metals to the luminous permanence of the noble ones. They were not entirely mistaken in thinking matter could change. They were simply working with the wrong tools centuries too early. For alchemists, the universe was filled with hidden sympathies and secret correspondences. They imagined metals as being part of a grand ladder of perfection, with lead and tin low on the rungs and gold and silver shining near the top. If you could only find the philosopher's stone, the mythical catalyst of transformation, you could climb that ladder, lifting matter up from its imperfect state into eternal brilliance. Gold was not just wealth to them, it was the very image of incorruptibility, a physical expression of the sun's perfection on earth. To turn lead into gold was, in a sense, to bring the sun's divine fire down into your own crucible. It is easy to smile at these ambitions today, to think of them as quaint or misguided. But there was a kind of poetry in their striving. Imagine the longing they must have felt, watching the sun blaze in the sky, believing that its radiance had a counterpart hidden within the earth, waiting to be released. Every hammer strike on a lump of ore, every hour spent boiling strange powders, was a gesture of faith that the world was not fixed, that matter could be persuaded to reveal new possibilities. Alchemy was part science, part spirituality, part dream. And in its way, it carried forward the same impulse that drives science today, the refusal to accept the surface of things as final. Among the many tales of alchemy, one story stands out, both tragic and instructive. In the late 18th century, James Price, a respected English chemist, announced that he had discovered a way to transmute mercury into gold. He demonstrated his process to eminent witnesses, claiming that a mysterious powder could effect the transformation. At first, he basked in recognition, but as skepticism grew, he was pressured to repeat his results before the Royal Society. When he failed to reproduce his miracle, his reputation crumbled, and in despair he ended his life. It is a painful reminder that the boundary between hope and humiliation in science can be razor thin, and that sometimes dreams become unbearable when they collide with reality. Price's story was not unique, though his ending was unusually dark. Throughout Europe, alchemists, both famous and obscure, spent fortunes and lifetimes chasing the elusive transformation. Many failed, but in their fumbling experiments, they invented tools and techniques: distillation, crystallization, the careful observation of chemical reactions that would later serve real chemistry well. In this sense, alchemy was not wasted effort. It was the apprenticeship of science, a childhood filled with myths and metaphors that would eventually mature into the discipline of chemistry and physics. Consider the language of alchemy, philosopher's stone, elixir of life, transmutation. These phrases sound like they belong in fairy tales, yet their essence persists in modern physics. Today, when we split an atom or fuse hydrogen into helium, we are performing the very transformations alchemists could only dream of. We are moving one element into another, rearranging the deep architecture of matter. It is not done with powders or mystical stones, but with the energies of particles, accelerators, and nuclear furnaces. The dream was real, though the method was different. The desire to make gold has not entirely disappeared either. In fact, modern science has succeeded in transmuting other elements into gold using nuclear reactions, though the process is so costly and inefficient that it could never rival a mine. A few atoms of gold created in a laboratory carry no practical wealth, but they carry symbolic meaning. The alchemists were, in some sense, vindicated. They were not wrong to believe that matter could be changed, only wrong about how. What is most striking when we think of alchemy is not its failures, but its continuity with our own age. The alchemists worked in dim workshops with furnaces and strange powders. We work in gleaming laboratories with particle colliders and superconducting magnets. But the question is the same. Can matter become something more than it seems? Can the hidden fire of the universe be coaxed into revealing its secrets? The philosopher's stone was never found, but in its place we have equations, theories, and experiments that have shown us the real transmutations at the heart of stars. There is also something deeply human in the longing to change lead into gold. It is not only about riches, it is about hope that the world itself is pliable, that nothing is entirely fixed, that imperfection can become perfection. When we gaze at the sun today and know that hydrogen is becoming helium in its core, that the very identity of atoms is being reshaped, we are seeing the true philosopher's stone at work, a natural process that has been happening for billions of years. The alchemist's dream was not wrong, only misplaced. So as you rest tonight, Picture those ancient experimenters hunched over their furnaces, the air filled with smoke and the smell of burning metals, their notebooks crowded with symbols that mingled the mystical and the practical. Picture their hope, their despair, their persistence, and remember that from their dreams, however misguided, came the roots of the science we now rely on to understand the stars. Alchemy was not a detour, but a prologue, a prelude to a deeper discovery. And in their longing for gold, they unknowingly pointed us towards something even greater. The fire in the hearts of stars, the true forge of the universe, where matter really does become something new. By the time the 18th century gave way to the 19th, the glow of alchemy had begun to fade. The philosopher's stone, once the object of countless dreams and desperate experiments, had receded into the realm of legend, while chemistry, careful, precise, sceptical, stepped forward to take its place. The new chemists were not searching for magical powders or elixirs of immortality. They were searching for patterns, for rules, for the quiet consistency hidden within the bewildering variety of substances, where alchemists had filled their notebooks with symbols half poetic, half practical. The chemists of this new age began to speak in numbers and laws, in tables and experiments that could be repeated by anyone, anywhere. The transformation from alchemy to chemistry is sometimes portrayed as a clean break, but in truth it was gradual, like dawn spreading across a night sky. Many of the early chemists still spoke the language of alchemy, still carried its hopes and metaphors, but their methods grew sharper. Antoine Lavoisier, often called the father of modern chemistry, demonstrated that matter is not lost in reactions but merely rearranged. His experiments with carefully weighed gases and burning metals revealed that the old belief in substances disappearing or being consumed was an illusion. What we call burning was not matter vanishing into nothingness, but matter combining with air, taking on new form. It was not alchemical magic, but arithmetic precision, a balance of weights that showed the hidden order of nature. This shift was monumental, because it meant that matter could no longer be thought of as endlessly mutable in the way alchemists once imagined. Lead could not become gold simply because one willed it so, or stirred the right powders in the right vessel. Each substance had its own identity, its own number of atoms, its own fixed structure. The dream of arbitrary transformation gave way to a new question. If elements are fixed, what gives them their character? Why is gold golden, iron strong, oxygen airy? The world was not a sliding ladder of perfection, but a puzzle of individual pieces, each locked in place yet capable of forming countless compounds in combination. And yet, beneath the discipline of this new chemistry, the longing for transformation never truly vanished. It simply moved into deeper territory, down to the smallest scales of matter. If chemistry could not transmute one element into another, perhaps something even smaller, hidden within the atom, could provide the key. Here we enter the threshold where chemistry gave way to physics, where the study of matter's outward behaviour led to questions about its inner heart. The atom, long imagined but not yet fully understood, became the focus. Early models portrayed it as indivisible, a fundamental grain of nature. But experiments began to whisper that this was not so. Atoms could emit strange rays, invisible but powerful, that could fog photographic plates and pass through flesh. Henri Becquerel discovered this with uranium salts. Marie and Pierre Curie pursued it with radium, isolating substances that glowed with their own strange light, evidence of energies trapped deep inside matter. What the alchemists had sought in vain with their furnaces and crucibles was in fact real. Matter did contain the possibility of transformation, but it was not the kind of transformation that powders or potions could bring. It was a transformation born of nuclear forces, far stronger and stranger than anything imagined before. The turning point came with Ernest Rutherford, whose experiments peeled back the veil on the atom structure. Firing alpha particles at thin sheets of gold foil, he expected them to pass through like bullets through mist. Instead, some bounced back as if they had struck something dense and unyielding. From this, Rutherford concluded that atoms were not uniform clouds but tiny solar systems, with most of their mass concentrated in a central nucleus. It was a revelation. The atom was not indivisible. It was a miniature world, with parts that could move, collide, and even change. From here, the possibility of true transmutation became more than dream. Rutherford himself achieved it, bombarding nitrogen with alpha particles and producing oxygen. At last, the age-old alchemical ambition to change one element into another had been realized. Not by philosopher's stone, not by mystical powders, but by physics, by the deliberate probing of the atom's inner structure. What James Price had claimed and failed, what countless alchemists had hoped for, Rutherford demonstrated in a laboratory. The curtain had lifted. The secret fire inside matter was real. Yet there is something important to notice here. While alchemy had sought transformation to create wealth or immortality, modern physics revealed it as part of nature's ordinary story. Atoms do not sit forever unchanged. They decay, they transform, they release energy, and they fuse into new forms. The universe itself is an alchemist, endlessly rearranging its ingredients. Radioactive decay turns uranium into lead. Fusion in stars turns hydrogen into helium and heavier elements. Fission splits heavy nuclei into smaller ones. These processes are not miracles, they are the daily business of the cosmos. For humanity, realizing this was like stepping into a new landscape. The philosopher's stone was not a single object, but the laws of physics themselves, written into the architecture of atoms. The alchemist's dream had always been about the possibility of change, the refusal to accept permanence. Physics showed that change was inevitable, woven into the fabric of matter itself. It is difficult to overstate how profound this shift was. Imagine standing at the edge of a forest, thinking you know its boundaries, and then discovering that it stretches on without end, filled with hidden valleys and rivers. That is what happened when matter revealed its nuclear heart. A new world opened, one that contained both promise and peril, for the same discoveries that explained the light of stars also laid the foundation for nuclear weapons. The sun's secret fire could be harnessed, but it demanded responsibility. Still, in the quiet of reflection, it is worth holding on to the continuity of the story. From the smoky chambers of alchemists to the precise laboratories of physicists, the longing was the same. To understand transformation, to glimpse the hidden fire that makes matter more than static. The dream that once drew figures into despair or delusion found its fulfillment in equations, accelerators, and reactors. And though the language changed, the wonder remained. So when we look back at the moment chemistry gave way to physics, we should see not a break but a deepening. Alchemy's metaphors matured into measurement, its myths into models, its failures into foundations. In seeking to turn base metal into gold, humanity stumbled instead into the far greater treasure, the realization that the universe itself is a furnace of transformations, that matter is not fixed, but endlessly reborn. In that realization, the sun's fire and the alchemist's dream finally came together, not as fantasy, but as fact. When people first peered into the atom, they expected to find simplicity, a kind of final grain of matter, smooth and unyielding. What they found instead was a furnace, a hidden chamber of extraordinary energies, capable of transformations that dwarfed anything imagined by the old alchemists. Inside the nucleus, where protons and neutrons cluster together in a knot of unimaginable density, lie the true fires of nature. They are fires that do not burn with flames or smoke, but with processes subtle and strange, processes that quietly shape the destiny of stars and the very fabric of the universe. These processes can be thought of as three great recipes of transformation: decay, fission, and fusion. Each recipe has its own rhythm, its own flavour, and its own consequences. The first recipe, radioactive decay, is perhaps the quietest. It is the slow whisper of the nucleus, releasing fragments of itself over time. Imagine a candle that does not simply extinguish when its wax is gone, but that instead sheds tiny sparks, one by one, until its substance is gradually transformed into something else. Heavy nuclei like uranium are unstable. They shed particles, sometimes an alpha particle, a pair of protons and neutrons bundled together, sometimes a beta particle, a nimble electron born of change within, sometimes a burst of gamma radiation, a pure pulse of energy. Each act of decay is small but cumulative, reshaping the nucleus step by step, like a sculptor chipping away at stone until a new form emerges. To us, these emissions may seem invisible, intangible, yet they are the ticking heartbeat of geology itself. The warmth of the Earth's interior, the slow shifting of continents, the very presence of certain elements beneath our feet, all are driven by radioactive decay. The second recipe is fission, and it is more dramatic. Here, a heavy nucleus does not merely whisper away pieces of itself, but splits apart in a sudden division, like a log cracking under pressure or a ripe fruit bursting open. When uranium or plutonium nuclei are struck just right, they cleave into smaller fragments, releasing energy and additional neutrons that can in turn split other nuclei. This is the principle behind nuclear reactors and, tragically, nuclear weapons. The chain reaction, a cascade of divisions that feeds on itself. The energy released is staggering, millions of times more than a chemical fire, energy that can boil water for electricity or devastate entire cities. Yet fission is not only a human invention, it occurs naturally too, though rarely. In the rocks of Gabon, Africa, scientists discovered fossilized natural nuclear reactors, places where uranium deposits had once achieved the right conditions for self-sustaining fission reactions nearly 2 billion years ago. Imagine it. Deep in the earth, long before humans existed, nature itself built a reactor, running silently for hundreds of thousands of years. But it is the third recipe, fusion, that lies at the heart of our cosmic story. Fusion is the joining together of light nuclei, the knitting of protons into heavier forms, the alchemy of stars. If fission is the splitting of wood, fusion is the kneading of dough, bringing small things together into something larger, releasing energy in the act of uniting. At the core of the sun, where temperatures soar to millions of degrees and pressures crush matter with relentless weight, hydrogen atoms are pushed so close together that they overcome their natural repulsion. Protons, normally like two magnets forced to touch at the same pole, finally merge, fusing into helium. This process releases energy that spills outward as light and warmth. The gentle rays that touch your skin on a spring morning. The glow that has nurtured life on Earth for billions of years. Fusion is the reason stars shine, the reason galaxies are lit, the reason the universe is not cold and dark. It is the most common alchemy of all, quietly working in countless suns across the night sky. And yet, for all its universality, it is delicate. Stars must balance fusion's energy against gravity's pull. If fusion slows, gravity wins and the star collapses. If fusion surges, the star may blow itself apart. Every star is a tightrope walker, poised between implosion and explosion, sustained by fusion's steady fire. These three recipes, decay, fission and fusion, are not separate curiosities, but parts of a continuum. They are the ways matter evolves, the ways energy and identity flow through the cosmos. In decay, we see the patience of transformation, nuclei slowly finding stability. In fission, we see the suddenness of division, energy unlocked in an instant. In fusion, we see creation, light born from the union of the smallest building blocks. Together they form the rhythm of cosmic cooking, the hidden alchemy that turns chaos into structure, that produces the elements of air, stone, water, and flesh. For us, these processes are not only scientific explanations, they are metaphors for life itself. Decay is the slow change we see in ourselves, in mountains weathered, in memories fading, transformations gentle and inevitable. Fission is the sudden breaking apart of what seemed whole, the abrupt changes that divide and redefine. Fusion is the opposite, the coming together of small things into something larger, a family, a community, a star. When you look at them this way, the fire of the nucleus is not distant. It is mirrored in the rhythms of human experience. It is humbling to think that what the alchemists once sought in their crucibles, the power to change matter, was hidden all along in the cores of atoms, quietly at work beneath our feet and above our heads. Radioactive decay warms the earth. Fission provides energy in our reactors. Fusion fuels the stars that scatter light across the night sky. The universe itself has always been an alchemist, and we are the students, slowly learning its recipes. So as you drift further into this story, let yourself imagine these fires not as violent or frightening, but as part of a cosmic kitchen. The universe stirs, splits, and fuses, trying combinations, discarding others, until the ingredients of life itself emerge. It is not a hurried process. It is slow, patient, balanced, and astonishingly effective. Out of invisible nuclei, it produces everything visible. Out of hidden fire, it produces the gentle warmth of sunlight on your face. And out of the simplest recipes, decay, fission, fusion, it produces the richness of the world we know. By the dawn of the 20th century, the question of the sun's energy had grown urgent. Astronomy had matured, geology had revealed that the Earth was far older than the few million years allowed by older theories, and biology, under Darwin's influence, required vast stretches of time for evolution to unfold. The sun had to shine not for thousands or millions, but for billions of years. Yet none of the explanations so far, burning coal, gravitational contraction, could keep its light alive for nearly so long. The puzzle remained, gnawing at the edges of science, a soft contradiction between the deep time demanded by Earth's history and the shorter time suggested by physics. It was in this tension, in this widening gap between what must be true and what seemed possible, that a quiet, brilliant voice spoke up. Arthur Eddington was not only an accomplished astrophysicist, but also a dreamer of sorts, a man who could look at the stars and see more than points of light. He believed the universe held secrets that could be uncovered with patient reasoning, even when the evidence was still incomplete. In 1920, at a meeting of the British Association for the Advancement of Science, Eddington stood before his peers and suggested something astonishing. The sun shines because hydrogen nuclei are being fused into helium. It was a bold leap, at once simple and staggering. At the time, the idea of nuclear fusion was still barely understood. The nucleus itself had only recently been revealed, thanks to Rutherford's experiments. Protons and neutrons were still mysterious characters on the stage of physics, and the forces that could hold them together, or press them into new arrangements, were not yet fully mapped. Yet Eddington's insight was both daring and elegant. He reasoned that the sun's energy must come from the transformation of matter itself, and that Einstein's new equation E equals mc squared provided the key. A small loss of mass during the fusion of hydrogen into helium could yield immense amounts of energy, enough to power the sun for billions of years. Imagine the courage it took to say such a thing aloud. There was little experimental proof at the time, only the intuition that the numbers fit, that the logic of nature pointed in this direction. Eddington wrote that if indeed 4 hydrogen nuclei could be combined into one helium nucleus, The difference in mass would be transformed into radiant energy. He called it a subatomic energy, and while the details were beyond the physics of his day, the vision was clear. The sun, he proposed, was a star-sized alchemist, fusing the simplest element into something heavier, and in the process releasing the light that bathes the earth. To grasp how extraordinary this was, picture yourself in that moment. The sun, long worshipped as divine, long puzzling to scientists, suddenly revealed as a furnace of nuclear reactions. The coal theory, the contraction theory, all swept aside by the realization that matter itself could be transmuted in the heart of a star. It was as though the universe had whispered its secret, and one attentive listener had heard it. The beauty of Eddington's leap is that it was not a guess pulled from thin air. It was grounded in the quiet arithmetic of nature. Einstein's equation had already shown that mass and energy are two sides of the same coin. Eddington simply extended that logic into the sun, asking what would happen if the atoms themselves were not fixed, but could merge and release their hidden store. And in doing so, he solved the riddle that had plagued scientists for centuries. How can the sun shine for billions of years without exhausting itself? The answer was simple and grand. It is not burning fuel in the way a campfire does. It is turning matter into energy, endlessly weaving hydrogen into helium, like a loom creating fabric from the thinnest threads. It took decades for the details of nuclear fusion to be fully worked out. Hans Bethe and others later explained the specific cycles, the proton-proton chain, the carbon-nitrogen-oxygen cycle, that power different kinds of stars. But the foundation was Eddington's. He had glimpsed the heart of the matter before the machinery was known, sketching the outline of a truth that would transform astrophysics. There is a quiet lesson in this story, one worth holding on to as you drift into stillness. Discovery does not always arrive as thunder, as sudden undeniable proof. Sometimes it arrives as a whisper of possibility, a leap of logic that bridges what we do not yet know. Eddington did not see fusion happen. He could not measure it directly, but he believed the sun's mystery demanded a new answer, and he trusted the harmony of nature to guide him. Today, when we say the sun shines by fusion, it sounds like an established fact, almost obvious. Yet a century ago it was daring, and it is worth remembering how strange it must have sounded then, that the most ordinary substance in the universe, hydrogen, could be transformed into helium, and that this transformation could light up the sky for billions of years. It is almost mythic in its simplicity, a new creation story told in the language of physics. So as you lie back and listen, think of Eddington not just as a scientist, but as a dreamer who looked at the sun and imagined the impossible, and then realised that the impossible might be true. Think of hydrogen atoms pressed together in the heart of the sun, like grains of flour kneaded into bread, producing warmth for planets, for oceans, for you. And think of the way a single insight can change everything. How one leap of thought can illuminate the darkness not only of the sky but of human understanding. The sun's mystery was solved not by firewood, not by shrinking spheres, but by the quiet fire of fusion, revealed in a moment of clarity. That was Arthur Eddington's gift to us, the leap that turned the sun from a puzzle into a poem written in nuclear light. Once Eddington had suggested that the sun's endless glow was born of fusion, the imagination of humanity began to wander toward a new possibility. If the stars lived by knitting atoms together, then perhaps we too might one day borrow that recipe and light our own hearth with the same inexhaustible fire. To think that a power so vast could be coaxed into a laboratory or held in a machine was both audacious and alluring. It promised energy without end, a warmth drawn not from dwindling wood or fragile coal, but from the very principle that kept galaxies shining. And so began the long story of our attempt to bring a star down to Earth. The first steps were tentative and theoretical. physicists tried to imagine what conditions were necessary for hydrogen to fuse, and the answer, as always, was daunting. Fusion requires not just warmth, but temperatures of millions of degrees, far hotter than any flame on Earth, hot enough to strip atoms bare of their electrons and to drive nuclei into each other despite their fierce repulsion. Protons are like identical magnets refusing to touch, and only when they are hurled together with overwhelming force will they merge. Recreating such a furnace on our planet seemed almost absurd. Yet once the secret was known, how could curiosity resist? In the middle of the 20th century, fusion was first glimpsed not in peaceful laboratories, but in weapons tests. The hydrogen bomb, unimaginably destructive, proved that fusion could indeed be unleashed, but only as a burst of devastation. It was as if humanity had stolen a star's spark only to drop it on cities. The paradox was cruel. The sun's gentle fire that nourishes life had been turned into a weapon of death. And yet, even amid the terror, scientists quietly held on to a different dream. That fusion could also be tamed, sustained, and made to serve life rather than destroy it. The challenge was containment. How do you hold a piece of starfire without letting it escape or consume its container? Imagine trying to bottle lightning, not once, but continuously. Ordinary materials would melt, vaporize, or disintegrate at such temperatures. So researchers turned to magnetic fields, invisible cages that could bend and trap the charged particles of superheated plasma. Machines called tokamaks and stellarators, with their elegant coils and looping chambers, became the laboratories of star power. Inside their vacuum-sealed vessels, hydrogen gas could be heated until it glowed like the aurora, swirling in magnetic embrace. For moments at a time, fusion reactions flickered into being, small echoes of the sun's heart, fragile and fleeting. Elsewhere, scientists tried a different path: lasers. At facilities such as the National Ignition Facility in California, enormous arrays of laser beams converged on tiny pellets of hydrogen fuel, crushing them with a light so intense it could rival the conditions of a star. The idea was to squeeze the fuel so tightly, so suddenly, that fusion would spark before the pellet could tear itself apart. It was not unlike striking flint with steel, trying to catch the brief flash and feed it into a flame. And slowly, after decades of trial and error, the results began to approach ignition, the point at which the fusion reaction produces more energy than was put in to spark it. Imagine the hope bound up in these experiments. To succeed would be to hold the power of the stars in human hands, not as a weapon, but as a wellspring of light. Fusion fuel, hydrogen, deuterium, tritium, is abundant, found in water and in the very fabric of matter. Unlike fossil fuels, it would not choke the skies with smoke. Unlike fission, it would not leave long-lived radioactive waste. It would be clean, nearly limitless, as close to perfect as any source of energy can be. The dream is so beautiful that it has survived failure after failure, decade after decade, like a lantern carried through long nights, always flickering but never extinguished. Still, the challenges remain steep. Containing plasma that is hotter than the core of the sun is a delicate dance. The fuel must be heated, confined, and sustained with exquisite precision. A stray instability, a ripple in the magnetic field, and the plasma collapses, vanishing like mist. Achieving net energy is only the first hurdle. Building reactors that can do it reliably, day after day, is a challenge still ahead. And yet, progress continues. In France, the ITER project is rising, a massive international collaboration that seeks to build the largest tokamak ever, a machine that could demonstrate sustained fusion at a scale never before attempted. Around it gather scientists from across the world, united by the shared hope of kindling a star on Earth. There is a certain poetry in this ambition. Humanity, born under the sun, has always turned toward it, for warmth, and direction. We tracked its path with sundials, honoured it with myths, painted its light in art. Now, in laboratories and reactors, we seek not only to bask in its rays, but to imitate its heart. It is as if, after thousands of years of worshipping the sun as a god, we now attempt to learn its craft, to bake our own bread from hydrogen and helium. We do not yet know if we will succeed, but the attempt itself speaks of our restless curiosity, our refusal to be content with shadows when we can chase the source of light. As you let this story settle, picture the quiet hum of those vast machines, coils glowing, magnets humming, plasma swirling like a captured aurora. Picture the scientists watching their instruments, waiting for the moment when energy flows outward more freely than it flows in, when for the first time on Earth, fusion is not only lit but sustained. It is a dream that has carried us from the myths of Helios and Ra, through the equations of Einstein and Eddington, into the steel and magnets of ITER. It is the same dream at heart, to understand the fire of the sun and to share in its power. One day, perhaps, we may look back and see this as the moment when humanity crossed a threshold, when the light of the stars became not only something to admire, but something to hold. Until then, the dream continues, steady and persistent, a spark carried forward through generations, waiting to become a flame. It is one thing to imagine fusion as a scientific puzzle, a challenge of magnets and lasers and equations, but it is another to imagine what it would mean if that puzzle was solved, if humanity truly learned to tend a flame drawn from the same hearth as the stars. The promise of fusion lies not just in watts and megawatts, in kilowatt hours stored and sold, but in the transformation of our relationship with energy itself. For all of history, we have lived as gatherers of fuel, wood piled into hearths, coal shoveled into furnaces, oil and gas drilled from beneath the seas. Even nuclear fission, though potent, is a process of splitting heavy atoms mined from rare deposits. Fusion would be different. It would be a shift from gathering to creating, from scraping fuel from the earth to coaxing fire from the most ordinary element in the universe. Consider the fuel itself. Hydrogen is everywhere. It whispers in every drop of water, a companion bound to oxygen in the oceans that cover our world. In its heavier forms, deuterium and tritium, it becomes the perfect candidate for fusion, able to merge with astonishing efficiency. Deuterium in particular is so abundant that a single litre of seawater contains enough to power a person's entire lifetime of energy needs, if only we knew how to tap it. Imagine walking along a beach and realising that the waves breaking at your feet, if their hydrogen were harnessed, could light a city. It is a thought that feels almost impossible, and yet it is not fantasy. It is physics waiting for mastery. The practical consequences of such a breakthrough would be profound. Fossil fuels with their smoke and carbon could be left behind. Power plants could run without choking skies or warming seas. Nations could draw energy not from contested oil fields or fragile supply chains, but from the shared oceans, whose waters belong to all. The struggle over scarcity could soften into the confidence of abundance. Even space exploration would change, for fusion offers fuels light enough to carry and powerful enough to propel ships across the distances between planets, perhaps even between stars. A spacecraft driven by fusion could, in principle, turn the journey to Mars from a precarious months-long ordeal into something steadier and safer, opening the solar system in ways our ancestors could barely imagine. And yet, beyond the practical, there is the symbolic. To master fusion would be to stand alongside the stars as apprentices, no longer just recipients of their light, but participants in their labour. Imagine a future in which cities glow at night, with light not drawn from coal or oil, but from reactions identical to those in the sun. Every lamp, every train, every warmed room would be, in some small sense, an echo of starlight. Humanity itself would have joined the cosmic guild of creators, adding its own small fires to the larger blaze of the universe. Of course, we are not there yet, and the road ahead remains long. Containing plasma for minutes, hours, days at a time is still an unsolved challenge. Machines the size of cathedrals hum and strain to produce results that last for only seconds. Funding rises and falls with political tides, and every new milestone is met with both celebration and caution. It may be decades before fusion becomes not just an experiment, but a power plant, quietly feeding electricity into the grid. And yet, even in the uncertainty, there is something soothing about the persistence of the effort. Generation after generation of scientists has picked up the torch, refusing to let the dream fade. It is an act of patience as much as of discovery, a reminder that not all fires must blaze at once. Some fires are nurtured slowly, until the conditions are right for them to catch. If one day fusion does become part of daily life, the change may not feel dramatic. Lights will still switch on, trains will still run, ovens will still warm bread. But beneath the ordinary rhythms, everything will be different. The hidden cost of energy, the weight of pollution and scarcity will have lifted. Humanity will breathe a little easier, not only because the air is cleaner, but because the future feels more open. Children growing up in such a world might think it was always so, might not realise that for centuries we burned the remains of ancient forests and oceans just to power our days. They might look back on coal mines and oil rigs the way we look back on windmills or water wheels. Once useful, once vital, but no longer needed. There is, however, another kind of change that fusion would bring. Quieter, but perhaps even more profound. It would alter how we think of ourselves in relation to the universe. We have always been dependent on the sun, not only for warmth, but for food, for the cycles of weather, for the possibility of life itself. With fusion, we would no longer only receive, we would also emulate. We would carry the sun's craft into our own hands, not to replace it, of course, but to honour it, to learn from it, to extend its lesson. It would be a gesture of kinship, a way of saying that we too can turn hydrogen into light, that we are not only children of starlight but practitioners of it. And perhaps, in the end, that is the real future of fusion, not just the wires and grids, the reactors and turbines, but the quiet recognition that the same fire that shaped galaxies is now, in some small way, within our reach. To live in such a world would be to live with a new intimacy with the cosmos, as if the boundary between earth and sky had softened. When you turned on a lamp, you would not only be lighting a bulb, you would be calling upon the same process that keeps the stars alive. You would be participating in the same transformation that began in the first minutes of the universe, when hydrogen and helium were forged in chaos. So as you drift in thought, imagine a city of the future glowing at night, its power drawn not from coal or gas, but from tiny drops of hydrogen, coaxed into fusion in quiet reactors. Picture a spacecraft sailing outward, its engines lit by the same process that lights the Milky Way. Picture the sun above, shining as it always has, and picture humanity below, finally able to echo its fire. That is the promise of fusion. Not only an end to scarcity, not only a cleaner earth, but a deepened bond with the cosmos itself. It is a promise that continues to beckon, gentle and steady, like a star on the horizon that we have not yet reached but cannot stop following. When you look at the night sky, it is easy to imagine the stars as eternal, each one a fixed lamp burning in place forever. They seem unchanging, scattered across the heavens like glitter spilled on velvet. But this stillness is an illusion born of distance and time. Stars are not eternal. They are born, they live, and they die. And in dying they give birth again, seeding the cosmos with the ingredients for new stars and new worlds. The sky is not a frozen canvas, but a living cycle, a rhythm of generations passing quietly in the dark. Astronomers have come to describe this cycle in terms of populations. It is a simple word, but it carries the weight of ancestry, of lineage stretching across billions of years. The first generation, population 3, were the pioneers. They were born when the universe was young, when only hydrogen, helium, and the faintest traces of lithium existed. These stars were massive, far larger than most of the stars we see today, and they burned with ferocity. Their lives were short, often just a few million years, mere flickers compared to the sun's billions. But their deaths were spectacular. They exploded in supernovae or collapsed into black holes, scattering the first heavier elements into space. We have never seen a population 3 star directly. They are long gone, their brief lives extinguished in the early chapters of cosmic history. Yet their fingerprints remain. The heavier elements they created, carbon, oxygen, nitrogen, iron, were not present before them. When we find these elements today, in planets, in living bodies, in the air we breathe, we are seeing the legacy of stars that lived and died before the Earth itself existed. They were the universe's first alchemists, forging complexity out of simplicity, shaping the raw hydrogen and helium into something more. After them came population 2 stars, born from the enriched clouds left behind. They contained mostly hydrogen and helium still, but now salted with trace amounts of heavier elements from the ashes of their ancestors. These stars lived longer, some still shining today in the ancient halo of our galaxy, or in the crowded centres of globular clusters. They are like living fossils, their light carrying the memory of the early universe. Through them, we can glimpse how the cosmos matured, how it began to experiment with new recipes. If population 3 stars were the first bakers, working with little more than flour and water, population 2 stars were the ones who began to add salt, yeast, and spices, crafting more varied loaves from the same cosmic kitchen. Finally, we arrive at population 1, the stars of our own era. The Sun is one of them. Born some 4.6 billion years ago, it contains not only hydrogen and helium, but also a generous helping of heavier elements. Carbon for life, silicon for rocks, iron for blood, oxygen for breath. These are the stars that form planets, that give rise to chemistry complex enough to assemble into oceans, forests, and eventually conscious beings who look back at the stars and wonder about their origins. In a sense, we are not simply inhabitants of Earth, but inheritors of a lineage that stretches back through every previous generation of stars. It is a quiet but profound thought. Every atom of calcium in your bones, every atom of oxygen in your lungs, every atom of iron in your blood was forged in the heart of a star long before the sun was born. You are, quite literally, stardust, not as a metaphor but as a fact. When you breathe, you're inhaling the legacy of population 3 and 2 stars, particles once part of furnaces long extinguished, now cycling through the air and through you. The sky is not above you, it is within you. This cycle of stellar generations is what astronomers call cosmic recycling. The universe does not waste. Every explosion, every scattering of ashes becomes the seedbed of something new. Clouds of gas enriched by dying stars collapse under gravity to form new stars, and in the swirling disks around them, planets emerge. Some planets may remain barren, deserts of rock or gas. Others may cradle oceans, atmospheres, and the delicate chemistry that can blossom into life. It is an endless chain of inheritance, each link forged in the furnace of the stars. And yet, even in this cycle, one detail remains puzzling. Among all the elements, lithium refuses to follow the pattern. Population 3 stars may have produced almost none. Population 2 stars show less than expected, and population 1 stars, like our Sun, contain even less. Somehow, this fragile element has slipped through the net of recycling. While carbon, oxygen, and iron have grown more abundant with each generation, lithium has dwindled. a vanishing note in the cosmic symphony. It is as if the universe itself could not quite decide what to do with it. But for now, let us set lithium aside. Its mystery will return soon enough. Instead, linger on the thought of these generations. Picture the first stars blazing, immense and short-lived, scattering their remains like sparks. Picture the second generation rising from the enriched clouds, glowing with steadier light. Picture the sun itself, a third-generation star, calm enough to nurture planets for billions of years. And picture yourself, breathing in the stardust, carrying in your body the echoes of explosions that took place before Earth even had a name. When you look at the night sky, you're not just looking outward, you're looking backward into the lineage of stars that made you possible. You're gazing at your ancestors, not in human form but in cosmic form, in spheres of fire and clouds of dust. The universe has been recycling itself for nearly 14 billion years, and you are one of its latest creations. In that knowledge lies both humility and comfort. The humility of being small in a vast lineage, and the comfort of belonging to a story so much larger than yourself. If stars are the kitchens of the cosmos, then their deaths are the great feasts, moments when the ingredients they have carefully cooked for millions or even billions of years are spilled out into the universe in a single extravagant gesture. The quiet fusion that sustains them cannot last forever. Eventually the fuel runs low, the balance falters, and the equilibrium between gravity pulling inward and fusion pushing outward collapses. What happens next depends on the size of the star, but for the most massive, the end comes in an explosion so bright that it can outshine an entire galaxy. These explosions are supernovae, and though they mark the death of a star, they are also the birthplaces of heavy elements, and the beginnings of countless new stories. Imagine a star 10 or 20 times more massive than the Sun. For millions of years it has fused hydrogen into helium, then helium into carbon and oxygen, steadily climbing the ladder of elements. As its life progresses, it burns hotter and faster, each stage shorter than the last, until even iron begins to appear in its core. But here the process halts, for fusing iron consumes more energy than it releases. The star can go no further. Gravity, which has waited patiently through all these eons, now rushes in. The core collapses in an instant, protons and electrons squeeze together into neutrons, the density rising to levels beyond imagination. The outer layers rebound against this sudden collapse, blasting outward with such violence that the star tears itself apart. In a matter of seconds, material that has been locked in the heart of the star is flung into space, enriched with newly forged elements, a scattering of cosmic treasure across the dark. Supernovae are rare by human standards, perhaps one every 100 years in a galaxy like ours, but when they occur, they leave imprints that last for millennia. Ancient observers recorded bright new stars suddenly appearing in the sky, visible even in daylight, only to fade months later. The Crab Nebula, for instance, still glows as the ghost of such an explosion, witnessed in 1054 by Chinese astronomers and others around the world. Its delicate filaments of gas spread outward, glowing with the energy of the past, whispering of the giant that once lived there. But beyond the beauty, supernovae serve a deeper role. They are the universe's way of seeding the cosmos with elements heavier than iron. Gold, silver, uranium, and many others require the furious energies of these cataclysms to be created. Without supernova, the universe would be rich in hydrogen and helium, but poor in the ingredients that make up planets, oceans, and living creatures. When you wear a gold ring, you are carrying on your finger the memory of a star's death, an element born in a moment of violence and scattered into the interstellar medium long before Earth was formed. And there is another, even stranger source of cosmic riches, the collision of neutron stars. When massive stars collapse, they sometimes leave behind neutron stars, tiny, incredibly dense remnants only about 20 kilometers wide, but with more mass than the Sun. Imagine squeezing a mountain into a teaspoon, and you have some sense of their density. These objects, though small, are among the most powerful in the universe, and when two of them spiral together and collide, the result is an event of unimaginable violence. Such collisions are rare, but their fingerprints are unmistakable. In 2017, for the first time, astronomers detected both gravitational waves, the ripples in space-time predicted by Einstein, and light from a neutron star merger. What they saw confirmed what had long been suspected. These collisions forge enormous amounts of heavy elements, including gold and platinum, scattering them into the universe in dazzling sprays. In that one event, more gold was created than in all the mines of Earth combined. It is a sobering thought that the jewellery we treasure, the coins once used to anchor economies, the circuits inside our devices, all trace their origin back not just to stars but to their most dramatic deaths and collisions. The poetry of this process is quiet but profound. Death becomes creation. Collapse becomes renewal. Stars end their lives, and in ending them, they provide the raw material for future stars, planets, and perhaps even life. The universe is not wasteful. Every ending is folded into a beginning. The elements scattered by supernovae enrich the clouds that give birth to new stars. The gold from neutron star collisions may someday cool into the crust of a planet, to be mined by creatures who have no memory of its fiery origin. In this way, the cosmos recycles itself endlessly, a cycle of destruction and rebirth as steady as breathing. For us, the legacy is intimate. The oxygen in your lungs, the calcium in your bones, the iron in your blood. These were forged in ancient stars and flung into space in explosions that shook the fabric of galaxies. Each breath you take is laced with history, measured in billions of years. Each heartbeat echoes with the rhythm of stellar deaths. You are, in the most literal sense, a child of supernovae. And though we live our lives mostly unaware of it, every glance at the night sky is a reunion with our origins. So as you let your thoughts drift, picture the final moments of a massive star, its heart collapsing, its outer layers exploding outward in a halo of fire. Picture two neutron stars locked in a spiral dance, finally colliding in a burst of light and gravitational waves that ripple through space itself. Picture the elements scattering, cooling, drifting, eventually becoming part of planets, oceans, and the bodies of living beings. These are not just remote cosmic events. They are your inheritance, the reason you are here to think, to breathe, to dream. And in the quiet recognition of that, perhaps there is a kind of peace. The universe is vast, and its processes may seem violent or indifferent, but within them lies continuity, a gentle assurance that nothing is truly lost. The stars die, but their ashes become new stars. Elements scatter, but they gather again in new forms. Out of fire comes the possibility of forests, oceans, and mines. Out of collisions comes creation, and through it all the cycle continues endlessly, patiently, beautifully. When you look at the sun, rising faithfully each morning and tracing its arc across the sky, it is easy to think of it as something apart, a solitary being with no family tree, simply present as if it had always been there. Yet the sun has an ancestry, a lineage written in the atoms that burn within it, and in tracing that lineage we find ourselves drawn into the story of generations of stars that lived and died long before the Earth ever formed. The sun is not a lone flame. It is the child of countless fires that burned and ended, a descendant of explosions scattered. Across the galaxy, a gathering of stardust pulled back together by gravity's hand. About 4.6 billion years ago, in one quiet corner of the Milky Way, a cloud of gas and dust drifted between the spiral arms. It was not extraordinary at first glance, one of many clouds stretching across the galactic disk, but within it lay a richness, the debris of earlier stars, carbon, oxygen, silicon, iron and heavier elements, gifts from supernovae and neutron star collisions, were mixed into the hydrogen and helium that still dominated. Gravity, ever patient, began to pull the cloud inward. Perhaps a passing shockwave from a nearby supernova nudged it, compressing the cloud until collapse became inevitable. Slowly, over millions of years, the gas condensed, heating as it fell inward, forming a spinning disk. At its centre, a protostar grew brighter, denser, hotter, until fusion ignited. That star was the Sun, newborn from the ashes of its ancestors. Around it, the swirling disk flattened into a broad, rotating plane. Within that disk, dust grains collided, stuck together, and gradually built up into larger bodies, pebbles, boulders, planetesimals. Over time, these clumps coalesced into the planets, moons, asteroids and comets that make up our solar system. The Earth itself was stitched together from this material, a patchwork of cosmic fragments fused into a single world, and every fragment carried within it the record of its stellar origins. The iron in Earth's core was forged in supernovae. The carbon in its soil came from stars that had shed their outer layers. The gold hidden in its crust was created in neutron star collisions. Nothing here was truly new, everything was recycled. This perspective shifts how we see the Sun. It is not simply a source of light, it is a living link in a chain billions of years long. The hydrogen and helium that make up most of its mass are relics of the Big Bang, primordial ingredients left over from the first minutes of the universe. The heavier elements, less than 2% of the Sun's mass, are the inheritance of earlier stars, contributions from stellar death scattered into space and gathered here. When we say the Sun is a third-generation star, a population 1 star, we are really saying that it carries within it the memory of 2 previous generations, just as we carry the memory of our grandparents and great-grandparents in our genes. It is a comforting thought, this continuity. The Sun shines today because of the ashes of stars that no longer exist. Stars that lived their brief lives billions of years ago and ended in fire. Without them, the Sun would have been only hydrogen and helium, unable to host planets rich in carbon or oxygen, unable to seed life. Our very existence depends on the generosity of stars long gone. They did not know us, yet they prepared the way, filling space with the ingredients that would one day become oceans, forests and breath. Lithium, of course, tells a different story. Though predicted to have formed in the Big Bang, it seems to have vanished along the way, destroyed in the hearts of stars or hidden in ways we do not yet fully understand. In the Sun, lithium is scarce, its fragile atoms consumed in the intense heat. Astronomers puzzle over its absence, comparing theory with observation, finding that the numbers do not quite match. The Sun, like many stars, seems to have misplaced this particular inheritance. It is as though one heirloom from the family chest has gone missing, leaving a gap in the record. The mystery of lithium reminds us that even as we trace the ancestry of stars with confidence, there remain unanswered questions, quiet puzzles waiting for clarity. When you stand outside and feel the warmth of the sun on your skin, you are feeling the combined legacy of generations of stars. Each photon began in the sun's core, born of fusion, but the atoms that allowed the sun to exist at all were gathered from the remnants of other stars. The warmth on your face is a family story billions of years long, a story of death and rebirth, of scattering and gathering, of dust turned into fire, fire turned into dust, and dust turned into you. Imagine the sun not as a solitary lantern, but as one flame in a long chain of torches, each passed from one hand to another across cosmic time. Population 3 stars lit the first torches, short-lived but bright. Population 2 carried the flame onward, adding new elements to the light. Population Y, including our sun, continues the chain, shining not only with its own fire, but with the memory of those that came before. One day, billions of years from now, the sun too will exhaust its fuel and shed its outer layers, enriching the galaxy once more. And from that enrichment, new stars may form, new planets may arise, and perhaps new beings will look up at their sky and wonder, as we do, where their light comes from. The ancestry of the sun is, in truth, the ancestry of us all. We are not separate from this story. We are part of the same cycle, bound by the same inheritance. Every breath you take connects you to stars that exploded before Earth was born. Every heartbeat echoes with iron forged in ancient cores. The sun, our nearest star, is both our parent and our sibling, both the light that nurtures us and the product of older lights that once burned elsewhere. Its ancestry is our ancestry, and in its warmth, we feel the embrace of a family that stretches across the cosmos. When we try to imagine the early universe, our minds instinctively reach for images of fire and explosion, because that is how we think of beginnings: dramatic, noisy, chaotic. But the reality of the first minutes after the Big Bang is something stranger, both more violent and more delicate. It was a kitchen without a cook, a recipe without a recipe book, a place where raw ingredients collided in confusion and yet somehow managed to assemble into something enduring. The first, chemistry, did not happen in laboratories or in the minds of thinkers, but in the vast newborn expanse of the cosmos itself. At first, there was only searing energy. Space expanded at a furious rate, dragging matter with it. Temperatures were so high that no atom could hold together, and particles tumbled freely, protons and neutrons drifting like ingredients scattered across a countertop. For the first few seconds, it was impossible for them to form anything stable. The heat tore apart any bonds as soon as they were made. But as the universe stretched and cooled, just enough calm returned for the first nuclei to take shape. This is what scientists call Big Bang nucleosynthesis, though the phrase sounds colder than the reality. You might imagine it instead as the universe's first kitchen, in which only a few ingredients were available, and only a brief window of time was open to mix them. The menu was simple: hydrogen, helium, and a dash of lithium. And the recipe was written not in cookbooks, but in the physics of the strong nuclear force and the expansion of space-time itself. Hydrogen was the easiest dish to prepare, because it was simply a single proton, sometimes with a neutron to form deuterium, sometimes with two neutrons to form tritium. These light nuclei came together like the first bubbles in bread dough, forming wherever conditions allowed. Helium was a bit more complex, requiring two protons and two neutrons bound into a tidy cluster, but once formed, it was extremely stable, like a loaf that refuses to collapse in the oven. Helium would become the second great note in the cosmic recipe, durable and abundant. And then there was lithium, fragile and fleeting. In principle, the reactions of those first minutes should have left behind a small but noticeable amount of lithium. In practice, however, its production was precarious. Some was made, but much of it was destroyed almost as soon as it formed, undone by the very conditions that allowed it to exist. It was the spice added to the stew, only to be boiled away before anyone could taste it. The lithium problem that still puzzles astronomers today has its roots here, in the first kitchen of the universe, when a recipe that worked so well for hydrogen and helium seemed to falter for lithium. The timing of this cooking was critical. The universe expanded so quickly that only a few minutes were available for these reactions to occur. Had expansion been faster, nuclei might never have formed at all, leaving a universe of protons without chemistry. Had expansion been slower, more complex elements might have emerged immediately, changing the path of cosmic history entirely. Instead, the balance was just right. In 3 short minutes, the basic recipe of the cosmos was set. About 3/4 hydrogen, 1/4 helium, and a trace of lithium. That ratio, born in chaos, remains with us today, etched into the composition of stars, galaxies, and the interstellar medium. It is astonishing. To think how much depended on those minutes. The fuel for stars, the material for planets, the foundation of water and air, all of it traces back to the primordial broth stirred in the first heartbeat of the universe. Without abundant hydrogen, stars could not have formed. Without helium, stellar fusion might not have stabilized into long-burning furnaces. Without that delicate balance, the cosmos might have remained a sterile sea of particles, without structure, without light, without life. What makes this story more extraordinary is how we know it. We cannot return to those first minutes, yet the light that still fills the universe, the cosmic microwave background, bears the imprint of those primordial ratios. When astronomers measure the glow left behind from 380,000 years after the Big Bang, they see the fingerprints of hydrogen and helium woven into it. The predictions of Big Bang nuclear synthesis match the observations almost perfectly, giving us confidence that this ancient kitchen really did prepare the universe's first ingredients in exactly the way physics describes. Only lithium remains the exception, a missing spice that has left us with one of the great puzzles of cosmology. To put this in more human terms, imagine baking bread and finding that every loaf comes out with the same consistent ratio of flour to water, no matter how many times you bake it. You would conclude that the recipe is sound, that the proportions are written into the process itself. But then, each time, you discover that the salt you carefully measured has somehow disappeared. The bread is good, but it is missing something. That is what lithium represents, a faint absence, a reminder that even in the most successful recipes, mysteries remain. When you look at the sun today, you are seeing hydrogen and helium still at work, the products of that first kitchen still being kneaded and baked into light. When you look at yourself, you are seeing those same elements transformed into life. Hydrogen flows through your veins in water molecules, helium has drifted into your lungs from the air, lithium helps regulate the chemistry of your brain. The universe's first cooking was not abstract, it was personal. Its flavours became our very being, and yet even with all our knowledge there is something soothing in the thought that the universe began with such simplicity. 3 minutes, 3 ingredients, 1 recipe. Out of that came everything. Galaxies, stars, planets, oceans, forests, mines. The first kitchen of the cosmos was not elaborate, but it was enough. And as you drift toward rest, you might think of it not as a violent explosion, but as the quiet opening of a recipe book, a cosmic baker kneading the simplest dough into the loaf of existence. The scent of it still lingers, not in air but in starlight, in every breath, in every heartbeat, in the calm persistence of the universe becoming itself. If the first 3 minutes of the universe were its kitchen, then the cosmic microwave background is its photograph album, a faded but faithful image that has survived across nearly 14 billion years. To look at it is to see the echo of creation itself, not in myths or metaphors but in light, stretched thin and softened by time until it whispers rather than shouts. And yet, that whisper carries more truth than volumes of books, for in its subtle patterns we find confirmation of the universe's earliest recipe and a reminder of the quiet mysteries that still linger, like lithium's absence from the expected list of ingredients. The story begins about 380,000 years after the Big Bang. Until then, the universe had been too hot, too dense, too crowded with free electrons to allow light to travel freely. Photons scattered constantly, bouncing from particle to particle like restless children in a crowded room, unable to slip away. The universe was bright on the inside but opaque from the outside, a fog of plasma where light was forever caught. Then, as expansion continued and temperatures cooled, electrons settled down, captured by nuclei to form the first true atoms. Suddenly, photons were released from their endless scattering. They streamed outward, free to travel through space without constant interruption. That moment is called recombination, but you might imagine it as the instant when a dense fog lifted, when light that had been trapped inside could finally spill into the open. That light has been travelling ever since, stretched by the expansion of the universe into the microwave region of the spectrum, cooled until it is now just a few degrees above absolute zero. It is everywhere, filling space with a faint glow, invisible to our eyes but unmistakable to our instruments. First discovered by accident in 1965 by Arne Penzias and Robert Wilson, who were puzzled by a persistent hiss in their radio antenna, the cosmic microwave background, CMB, has since become one of the most important discoveries in cosmology. What they thought at first was noise, perhaps pigeon droppings in the dish, turned out to be the oldest light we can see, a direct message from the infant universe. When scientists measured the CMB with greater precision, first with the COBE satellite in the 1990s, then WMAP in the early 2000s, and more recently with the Planck Observatory, they found that its faint glow was astonishingly uniform, the same in every direction to 1 part in 100,000. That uniformity told us that the universe really had begun with a hot, dense state, expanding evenly in all directions. Yet within that near perfection lay tiny ripples, slight variations in temperature, like the faint dimples in rising dough. Those ripples were the seeds of all later structure, the small differences that would grow into galaxies, stars, planets, and eventually us. Without them, the universe might have remained a featureless sea of hydrogen and helium, smooth and sterile. With them it became a place of diversity and beauty. The CMB also carries within it the fingerprints of the universe's first ingredients. By analysing its spectrum, scientists can confirm the relative amounts of hydrogen and helium predicted by Big Bang nucleosynthesis. And indeed, the match is almost perfect. The cosmos produced about 3/4 hydrogen and 1/4 helium, exactly as the theory said it should. This agreement is one of the triumphs of modern cosmology. The reason we can say with such confidence that our models of the early universe are sound. The recipe worked. The bread rose as expected, and yet, amid this confirmation lies a quiet discord. Lithium does not match. Theory predicts there should be 3 times more lithium in the oldest stars than what we actually observe. The CMB says the recipe included it, the calculations insist it was baked in, but the measurements of ancient stars whisper otherwise. It is as if the photograph of a family gathering shows a dish on the table, but when you search the leftovers later it is missing. Did someone remove it? Did it burn unnoticed? Or was it never served in the first place? The lithium problem remains unsolved, a small riddle left in the corner of an otherwise well-understood picture. There is something gentle and almost comforting about this imperfection. It reminds us that even the most precise sciences still leave room for mystery, that the universe never yields all its secrets at once. The CMB is a tapestry woven with astonishing precision, yet one thread remains loose, one knot untied. To fall asleep under such a thought is to be reminded that the universe is both knowable and unknowable, both explained and still waiting. Imagine lying beneath the night sky, knowing that the faint glow of the CMB passes through you even now. It does not stop at your skin. It seeps through walls, oceans, mountains, unimpeded. It is everywhere. A background hum of ancient light, a soft blanket that covers all of space. Though your eyes cannot see it, your body is bathed in it, just as every atom around you is. It is the universe's lullaby, still singing after billions of years. And in that song lies reassurance. The cosmos has a history, it has continuity, it has memory. The discovery of the CMB also changed our relationship with the cosmos. Before, cosmology was speculation mixed with mathematics, bold but fragile. After, it became something anchored, a field with evidence you could measure, photograph and analyse. It was as if the universe had finally offered us a diary page from its childhood, not written in words but in wavelengths, telling us what it was like before stars, before galaxies, before even the sun had been born. And though the handwriting is faint, the meaning is clear. Out of chaos came order, out of light came structure, and out of silence came a story we are still learning to read. So as you rest, think of the CMB not as an abstract concept, not as 3 words tucked into textbooks, but as the oldest light in existence, the first photograph of the universe's face. Think of it as a family portrait where hydrogen and helium sit proudly in the centre, lithium lingers on the edges, and everything else waits to be added later. Think of it as a reminder that the universe does not forget, that even after billions of years it keeps a memory of its first moments, glowing softly across the sky, invisible to eyes but unavoidable to instruments. And let that memory settle over you like a blanket, a comfort in knowing that you are living inside a story that began long ago, a story whose opening chapter is still shining, gently, all around you. Among the universe's family of elements, lithium is something of an odd child. Hydrogen is abundant and sturdy, forming the seas of gas that light stars and fill galaxies. Helium, though quieter, is stable, a noble partner that anchors both stars and balloons with calm reliability. But lithium is fragile, short-lived, difficult to hold on to. It is the spice in the recipe that never seems to stay in the pot, the heirloom passed down only to disappear before it can be displayed. To understand why lithium is missing, one must understand just how delicate it really is, how easily its bonds are broken, how quickly it vanishes under conditions that other elements survive with ease. Lithium's fragility begins in its structure. Its nucleus, containing 3 protons and usually 4 neutrons, is light enough to be disrupted by relatively modest temperatures. In stars, where the cores rise to millions of degrees, lithium is quickly destroyed. The fusion reactions that power stars are merciless to it. At about 2.5 million Kelvin, a temperature that sounds almost unimaginable, but is modest compared with the 15 million Kelvin of the Sun's core, lithium nuclei are broken apart, consumed in reactions that erase them before they can accumulate. Hydrogen can withstand these conditions, helium thrives under them, but lithium is undone, like a thin thread snapped by the slightest strain. In the Sun, lithium is present only in faint traces, its atoms steadily depleted over time. Other stars show similar patterns, especially those that are older or hotter. This makes lithium difficult to measure, and even more puzzling, because theory suggests there should be more of it preserved from the early universe. Instead, when astronomers examine ancient stars, those born soon after the Big Bang, stars that should carry pristine amounts of primordial lithium, they find only a third of the expected abundance. Somewhere along the line, lithium has gone missing, either destroyed in ways we do not fully understand, or hidden in places we have not yet learned to look. You might picture lithium as a delicate snowflake, beautiful in its formation but quick to melt under even a faint warmth. Hydrogen and helium are like icebergs, solid and enduring, but lithium is the flake that disappears on your glove before you can show it to a friend. The cosmos seems to produce it, but then promptly erases it, leaving only whispers behind. This is why astronomers speak of the cosmological lithium problem, because it is not just a matter of numbers, but a matter of fragility, a mismatch between what should exist and what we can see. The problem becomes even more interesting when we consider where lithium does appear. It is not entirely absent. On Earth, lithium is mined and used in batteries, in medicine, in alloys. It accumulates in rocks and in brines, concentrated by geological processes. Its presence here is not from the Big Bang alone, but from a mixture of cosmic sources. Some lithium is created later in the lives of certain stars, in red giants where unusual conditions allow fresh lithium to be produced and then shed into space. Some is created by cosmic rays, high-energy particles colliding with atoms in interstellar space, shattering heavier elements into lighter ones, lithium among them. So lithium is not a one-time product. It has a complicated life story, appearing and vanishing, destroyed in some places and recreated in others. This complexity adds to the puzzle. If lithium can be both created and destroyed in multiple ways, then tracing its cosmic history becomes like following a fragile thread through a labyrinth, always at risk of breaking, always leaving gaps. Some researchers suspect that the missing lithium may be locked away in the interiors of stars, drawn downward by convection and consumed where we cannot see it. Others wonder if our nuclear physics calculations, though precise, may still hide small uncertainties that grow into large discrepancies. A few even suggest that lithium's mystery could hint at new physics, processes in the early universe that we have not yet uncovered. There is something strangely poetic about this fragility. Hydrogen and helium dominate the cosmos, reliable and abundant, yet lithium slips through our grasp. It is the note in the symphony that fades before the chorus begins, the guest who leaves the feast before the first toast is raised. Its very absence has become more interesting than its presence, because it reminds us that even in a universe we can measure with extraordinary precision, some questions remain open, some puzzles unsolved. For us on Earth, lithium has become both practical and symbolic. In batteries, it powers our devices, storing energy in ways that shape daily life. In medicine, it is used to stabilize fragile moods, a reminder that even in the human brain, balance can be delicate. The same element that puzzles cosmologists is also helping people on Earth find steadiness, a strange echo of fragility turned into usefulness. In this sense, lithium reflects both the cosmic and the personal, an element that is missing from the stars yet present in our hands and lives. So as you drift in thought, picture lithium not as an absence but as a whisper. Imagine it as a fragile thread in the cosmic fabric, one that frays easily but still holds enough to remind us of its presence. Think of the snowflake melting, the spice boiling away, the heirloom misplaced but remembered. Lithium's fragility is not a flaw of the universe, but part of its character, part of the way it teaches us that not all things are robust, that some are fleeting, and that their very fleetingness makes them precious. The puzzle remains unsolved, and perhaps it will be for some time, but there is no hurry. The universe has carried its lithium secret for nearly 14 billion years. It can keep it a little longer, and in the meantime the absence itself is a kind of presence, a gentle reminder that science, for all its triumphs, always leaves space for mystery. To lie beneath the stars and wonder where the lithium has gone is to participate in that mystery, to be part of the same fragile thread, delicate yet enduring, woven into the story of the cosmos. If you wish to listen to the oldest voices in the universe, you cannot find them in books, or in ruins, or in the traces of human history. You must look upward, into the faint glimmers of stars that formed long before Earth was born, stars so ancient they are sometimes called fossils of the cosmos. They live mostly in the halo of our galaxy, or in tight clusters where time seems to have slowed, their light dim but steady, unchanged for billions of years. These stars are poor in metals, as astronomers put it, meaning that apart from hydrogen and helium, they contain almost none of the heavier elements that later generations of stars would inherit. In their simplicity, they preserve the chemistry of the early universe, as though holding in their cores the record of the cosmos's childhood. For decades, astronomers have turned their telescopes toward these ancient stars, hoping to read that record. In their atmospheres, where material from deep inside has not yet been stirred or consumed, lies the imprint of the primordial elements forged in the Big Bang. The hope was simple: measure the hydrogen, helium and lithium in these stars, and you could confirm the predictions of Big Bang nucleosynthesis. Hydrogen and helium, as expected, lined up beautifully with theory. But when lithium's voice was sought, it came out faint, muffled, almost absent. The amount of lithium in these stars was only about 1/3 of what theory demanded. It was as if, in opening a long-lost manuscript, the pages describing Lithium's story had been torn away. This mismatch is what astronomers call the cosmological lithium problem. It is not a vast chasm. Hydrogen and helium still dominate as predicted, and the broad outline of cosmology stands firm, but it is an unsettling crack in an otherwise solid wall. Lithium should be there. The numbers from nuclear physics, the expansion rate of the universe, the delicate dance of protons and neutrons in the first minutes all say it must be. And yet, when the oldest stars are examined with care, it is missing. The library is intact, but the chapter on lithium has gone unreadable. For scientists who have spent their lives constructing precise models of the early universe, this absence has been troubling. Astronomy is, in many ways, a discipline of patience. Observations are gathered slowly across nights and seasons and generations. Patterns are teased out of faint signals. Correlations are built into laws. And so to encounter a puzzle that refuses to yield after decades of measurement is to feel a kind of stubborn silence from the cosmos, as if the stars themselves were withholding a secret. Imagine a grand library, one whose shelves stretch endlessly, filled with volumes bound in starlight. Each star is a book, its atmosphere inscribed with the chemical record of its birth. You walk along the aisles, pulling volumes at random, finding that most tell the story expected: hydrogen abundant, helium reliable, heavier elements increasing with each generation. But when you reach for the volumes that should contain lithium, you find the pages faded, the ink smudged, the script incomplete. It is not that the book is missing entirely, only that the passages you hope to read have grown illegible. The library is generous, but it is not entirely cooperative. Over the years, astronomers have refined their techniques, using larger telescopes, sharper spectrographs, more careful calibrations, hoping that perhaps the missing lithium was a mirage caused by faulty instruments. But the result has persisted. Whether in the light of halo stars and globular clusters, or even in some dwarf galaxies beyond our own, the lithium deficit remains. The numbers do not match. The stars continue to whisper hydrogen and helium faithfully, but when asked for lithium, they respond with silence. The puzzle is especially striking because the rest of cosmology has become so precise. The cosmic microwave background tells us the ratios of the early elements with extraordinary accuracy. The expansion of the universe is mapped with exquisite detail, yet this one element refuses to cooperate. It is like having a jigsaw puzzle with every piece in place except for one in the centre, the absence made sharper by the perfection of the rest. The missing lithium does not topple cosmology, but it nags, it unsettles, it keeps scientists awake at night staring at equations that refuse to close. For those outside astronomy, it may seem a small problem. What difference does it make if lithium is a little less abundant than expected? But in science, small mismatches matter. They are often the signs of deeper truths waiting to be uncovered. History is filled with such examples. The faint wobble of Mercury's orbit that hinted at Einstein's relativity. The unexpected behaviour of radioactive elements that led to quantum mechanics. A discrepancy is not just an error, it is an invitation. And so, lithium, with its faint and fragile absence, has become an invitation to think more deeply about stars, about physics, about the story of the universe itself. There is something quietly human in this search. We are drawn to completeness, to stories with no missing chapters, to melodies with no broken notes. When we encounter absence, we linger. We wonder what was supposed to be there, what we are not being told. The lithium problem is, in this sense, a cosmic mirror of our own tendencies. It reminds us that the universe is not obliged to satisfy our desire for neatness. Sometimes it withholds. Sometimes it keeps a chapter half written, leaving us to imagine the missing words. So the oldest stars speak, but their voices are incomplete. They tell us most of the story we expect, but they leave lithium's tale unfinished. Their light reaches us after billions of years, bearing secrets from the dawn, but when we try to read those secrets, the ink runs thin. It is a mystery that has endured not because it is grand, but because it is stubborn. A small silence that grows more profound the longer it lasts. And as you drift into rest, you might think of those ancient stars as a library glowing faintly in the dark, their shelves filled with knowledge, their pages whispering truths, yet with certain passages faded beyond recognition. We know the story is there, we just cannot read it all. When you come across a mystery in science, the first instinct is rarely to tear up the entire book and declare the story false. Instead, the instinct is gentler, more cautious. Perhaps the ink has smeared, perhaps the page has been damaged, perhaps the reader is misunderstood. And so, when astronomers confront the lithium problem, when they look at the ancient stars and find only a third of the lithium predicted by theory, they do not immediately assume the cosmos has betrayed them. They begin, as cooks might do with a stubborn recipe, by checking whether the measurements were wrong, whether the oven was too hot, whether the ingredients were miscounted. The first possible explanations are humble ones, grounded in the idea that the recipe is sound but that something in our reading of it has been blurred. The simplest suggestion is that the lithium is there but hidden. Stars are not static layers of gas, they are restless, convective, always stirring themselves. Material on the surface can be drawn downward into hotter regions where fragile lithium is quickly destroyed, then replaced by other material rising upward. If this happens over billions of years, the atmosphere of a star, the part we can see, may contain far less lithium than was originally present at its birth. The element would still have been created in the Big Bang, but it would have been erased by stellar processes before our telescopes could measure it. This is the stellar depletion hypothesis, and it has some elegance, for it does not require us to rewrite the early universe, only to accept that stars themselves have edited the record. But even this explanation has its complications. Stellar models do suggest that mixing and convection can reduce lithium, but not always to the degree observed, and not consistently across all old stars. Some ancient stars show nearly identical lithium abundances, as if they all followed the same rule, the same depletion. This consistency is puzzling. If convection alone were responsible, we might expect more variation, more scatter in the results. Instead, it is as though all the books in the library are missing the same chapter, torn out in the same way. That uniformity hints at something deeper than just stellar restlessness. Others have wondered whether the fault lies not in the stars but in our instruments. Spectroscopy, the technique by which we measure the chemical fingerprints in starlight, is delicate work. Absorption lines can be blurred, shifted, or confused by other processes. Might we simply be misreading the lines? Could the lithium be present, but its signals drowned out or misinterpreted? Astronomers have refined their methods over decades, improving their sensitivity, correcting for confounding factors, and yet the shortfall persists. It is as if the recipe book itself is smudged with flour stains, obscuring the exact measurements. No matter how carefully we squint, the number never seems to match. A more radical idea is that our nuclear physics might be incomplete. The reactions that produce lithium in the first minutes of the universe are simple enough to write down, but they depend on cross-sections and probabilities, numbers that describe how likely particles are to collide and stick together. These numbers are measured in laboratories on Earth, but what if they are not quite right under the conditions of the Big Bang? Could a subtle error in the nuclear reaction rates explain the mismatch? Experiments have tested this possibility, but the results suggest that the known physics is sound. The flour in the recipe is measured correctly. The yeast is behaving as it should. Still, the bread comes out different. There are even those who wonder whether new physics might be needed. An unseen particle, a previously unknown interaction that altered the balance in those first minutes. Such proposals are always tempting, for they offer the excitement of discovery, the chance to expand the laws of nature. but they are also risky. To invoke new physics is to change the recipe book itself, to suggest that the smudges are not from flour, but from a misprint, that the instructions themselves were written differently than we thought. Most scientists hesitate before making such claims, preferring to exhaust the more ordinary explanations first. Yet the possibility lingers, like the scent of something unidentifiable in a familiar dish, a flavour you cannot quite place but cannot deny. It is worth pausing here to appreciate the subtlety of the problem. The difference between prediction and observation is not enormous. It is a factor of 3. In daily life, we might shrug off such a discrepancy. If a recipe says a pinch of salt and we add half as much, the bread still tastes fine. But in cosmology, where predictions and measurements often match to extraordinary precision, sometimes to better than 1 part in 1,000, a factor of 3 is not trivial. It is glaring, like a stain on a white cloth, impossible to ignore. The lithium problem is small in scale but large in implication, a reminder that even tiny disagreements can ripple outward into questions about the whole. Perhaps the most poetic way to think of it is this. The universe handed us a recipe book at birth, its pages written in light and matter. Most of the pages are clear. Hydrogen, check. Helium, check. The measurements and the predictions align beautifully. But when we turn to lithium, the page is blurred, the handwriting uncertain, as though smudged by the hand of a baker covered in flour. We can see that something was written. We can make out the outline of the word, but the numbers are indistinct, the instructions ambiguous. And so, the bread we bake does not quite taste as we expected. The recipe works in every other respect, but this one detail refuses to settle. This is how science progresses, not by discarding the whole book when one page is smudged, but by rereading, by testing, by rewriting carefully when the evidence demands it. The lithium problem remains unsolved, but it is not a failure. It is an invitation to keep reading, to keep baking, to keep wondering whether the smudges from the baker's hand, the printer's press, or some deeper secret in the recipe itself. So as you drift tonight, imagine yourself in that kitchen with the ancient recipe book, its pages spread out before you. Most are clean, precise, clear, but one is blurred, covered in faint flour stains, the numbers hard to read. You try to follow the instructions anyway, and the bread comes out almost right, but not quite. The taste is close, but something is missing. That is the lithium problem, a faint imperfection in an otherwise exquisite recipe. A reminder that the universe still holds secrets in the margins. At first glance, the lithium problem may seem trivial. The universe is vast, filled with galaxies and clusters, woven together by filaments of dark matter, its expansion shaped by the mysterious push of dark energy. Against this grand backdrop, the fact that one light element is less abundant than expected by a factor of 3 might sound like a footnote, a detail too minor to trouble the mind. After all, the stars shine, the planets orbit, the galaxies dance across billions of years. Why should it matter that a trace element is missing? But in science, small cracks can reveal deep truths. Think of the orbit of Mercury, which for centuries seemed only slightly out of step with Newton's predictions. The discrepancy was tiny, measured in arc-seconds, almost invisible to the casual observer. Yet that tiny difference was a clue to the limits of Newtonian gravity, a crack that eventually opened the door to Einstein's general relativity. Or consider the faint hiss that Penzias and Wilson first dismissed as noise in their antenna, a hiss that turned out to be the cosmic microwave background, the afterglow of creation itself. Sometimes it is the small, stubborn detail, the one that refuses to fit, that carries the greatest significance. Lithium is such a detail. The universe is a precise machine. The equations of cosmology, when combined with the physics of nuclei, predict abundances of hydrogen, helium and lithium that should remain visible in the oldest stars. Hydrogen and helium line up beautifully with observation, a harmony that reassures us that our understanding is sound. But lithium breaks that harmony. Its voice in the cosmic choir is softer than it should be, as if one instrument has dropped out. And when one note is wrong in an otherwise flawless performance, it unsettles us, for it suggests that something in the score has been misread, or that some unseen hand is muffling the sound. One possibility is that the missing lithium simply reflects overlooked stellar physics, processes inside stars that deplete or hide it more effectively than we realise. This would be significant in its own right, reminding us that stars are not as simple as we sometimes imagine. They are not just spheres of gas burning steadily, but dynamic systems with convection, turbulence, mixing, magnetic fields, all of which can alter the chemistry we see on their surfaces. To solve the lithium problem by better understanding stars would deepen our knowledge of stellar life cycles, adding nuance to our picture of how they evolve and age. Another possibility is more unsettling, that the lithium problem hints at deeper flaws in our cosmological model. If our understanding of Big Bang nucleosynthesis is incomplete, if our calculations of nuclear reactions or our assumptions about the early universe are missing something, then lithium is the messenger pointing us toward that gap. Perhaps there were processes at work in the first minutes that we have not yet imagined, interactions with dark matter, for instance, or particles not included in our current physics. Perhaps the universe's first kitchen was more complicated than we think, with extra steps or ingredients not listed in our recipe. In that case, lithium is not just a puzzle but a doorway, inviting us to expand our physics, to reconsider our assumptions about how matter came to be. Even if the truth turns out to be mundane, the search itself is valuable. In chasing lithium, astronomers refine their instruments, improve their models, sharpen their theories. They become better readers of the cosmic text, more sensitive to its smudges and silences, and in the process, they remain humble before the universe, reminded that no matter how confident we grow, there will always be mysteries waiting, details that slip away, questions we cannot yet answer. There is also something symbolic in lithium's absence. It reminds us that perfection is rare, that even the most elegant theories have limits, that even the most precise models leave room for surprise. Science thrives not on certainty, but on uncertainty, not on the answers we already have, but on the questions that refuse to go away. The lithium problem is not an embarrassment. It is a gift, a reminder that the universe is still larger than our understanding, that there are still doors unopened, still rooms unexplored. You might think of it like a lantern with a single pane of glass missing. The lantern still gives light, the flame still burns, but the gap catches your eye. You wonder why it is there, whether it was broken or whether it was made that way. The missing pane does not extinguish the light, but it draws your attention, makes you notice what otherwise you might have taken for granted. Lithium's absence is the missing pane in the lantern of cosmology, the gap that makes us look closer, think harder, search further, and perhaps this is why it matters most. The lithium problem is not about lithium alone. It is about the attitude it inspires, the persistence of curiosity, the refusal to stop asking questions even when the answers are small or elusive. It is about the willingness to peer into the margins, to take seriously the details that do not fit. In this way, lithium is not just an element but a teacher, reminding us that the universe is not a solved puzzle but a living text, always ready to surprise us. So as you rest tonight, think of lithium not as a failure but as a promise. Think of it as the soft crack in the wall that lets in new light, the missing note in the song that keeps us listening. Think of it as the small riddle that ensures science never becomes complacent, that our models never grow too comfortable, that we never mistake knowledge for completeness. Lithium matters because it is small, because it is fragile, because it refuses to fit. And in that refusal it keeps us awake, keeps us wondering, keeps us alive to the mystery of the universe becoming itself. Long before telescopes, before laboratories, before equations written on chalkboards, humanity had another tool for understanding the cosmos: the story. Stories were our first models, our first theories, our first equations written not in numbers but in images, metaphors and memories. When we looked up at the sun, we did not measure its spectrum or calculate its fusion cycles. We told ourselves that it was a god in a chariot, or an eye watching over us, or a fire carried across the heavens each day. These stories were not childish mistakes. They were attempts to make sense of the overwhelming, to weave the unknown into something that felt familiar, to tame the chaos of the sky into a narrative that could be remembered and passed on. In Egypt, the sun was Ra, fierce and commanding, sailing his barge across the daytime sky and descending into the underworld each night to battle serpents before rising victorious again. The daily cycle of light and darkness became a drama of life and death, courage and renewal. In Greece, it was Helios, guiding his chariot of fire, horses galloping with sparks flying from their hooves, the sky itself a racetrack circled by divine endurance. In India, Surya rode with 7 horses, each representing a ray of light, illuminating the world with his steady gaze. And among countless other cultures, the Inca, the Norse, the Chinese, the sun was never just a ball of fire. It was a being, a companion, a presence woven into every harvest, every ritual, every prayer. These stories mattered because they gave order to what would otherwise have been chaos. Imagine living without clocks, without calendars, without the quiet hum of scientific explanation. You would watch the sun rise and fall, the seasons shift, the shadows lengthen or shorten. You would notice patterns, but you would need meaning to anchor them, to transform repetition into reassurance. Myth provided that meaning. It told you that the sun did not just appear and disappear at random, but that it followed a path, performed a duty, enacted a story larger than yourself. In those stories you could place your own life, your own fears, your own hopes. As centuries passed, those myths gave way to new forms of explanation. Yet the impulse was the same. When philosophers of ancient Greece began to ask whether the sun might be a sphere of fire rather than a god, they were not rejecting the need for story. They were simply writing a new chapter, turning the narrative toward reasoned speculation. When medieval scholars debated whether the heavens were crystalline spheres or infinite void, they were still telling stories, only now with geometry instead of gods. And when Copernicus, Galileo and Kepler reshaped our view of the solar system, they too were storytellers, offering new narratives of circles, ellipses and forces. Science did not erase story, it transformed it. In this way, science can be seen as the latest myth, not in the sense of being false, but in the sense of being a framework, a set of tales we tell ourselves to bring coherence to experience. Instead of chariots and serpents, we speak of fusion chains and convection currents. Instead of gods pulling the sun across the sky, we speak of nuclear binding energy and gravitational balance. The language has changed, but the need has not. We still seek order in chaos. We still shape the unknown into something we can live with. We still pass along these explanations as stories, now written in textbooks and articles, narrated in lectures and documentaries. Think of the lithium problem itself. To say that one element is missing to puzzle over why is already to tell a story. We have cast the universe as a cook, the stars as record keepers, lithium as a fragile heirloom misplaced in the shuffle of generations. These are metaphors, myths of our own making, woven not to deceive but to remind us that science too is a form of storytelling. The difference is that it is a story checked against evidence, revised with every new measurement, tested against the stubbornness of reality. But at its heart, it is still narrative. Beginnings, middles, endings, mysteries, resolutions, and sometimes cliffhangers that linger unresolved. There is comfort in realizing this continuity. When we tell ourselves that the sun shines because hydrogen fuses into helium, releasing energy that takes thousands of years to escape from its core, we are not speaking a language fundamentally different from those who said the sun was the eye of a god. We are simply speaking a newer dialect, one honed by instruments and mathematics. The awe is the same. The desire to explain is the same. The human heart, restless in the face of mystery, reaches for story, whether it is clothed in myth or in physics. So when you think of myths of the sun, do not dismiss them as primitive or outdated. Think of them instead as earlier verses in the same song. Verses sung by ancestors who gazed at the same light we see today, who felt the same warmth on their skin, who planted seeds under the same glow. Their stories were their way of keeping chaos at bay, of transforming the incomprehensible into something graspable. Our science is simply the latest verse, more precise, more predictive, but still sung with the same longing for order. And perhaps, in the quiet of the night, when you set aside equations and spectra, you can still feel the myth alive beneath the science. The sun still rises with the dignity of Ra, still rides with the vigour of Helios, still shines with the clarity of Surya. And when we say that it fuses hydrogen into helium, we are not cancelling those stories. We are layering them, adding detail to detail, weaving old myths and new science into one tapestry of understanding. In that way, the stories we told ourselves, and the stories we continue to tell, are not separate from science but part of the same human impulse. They are how we live with the mystery, how we anchor ourselves in the vastness, how we soften chaos into a narrative we can carry in our minds. And whether the sun is seen as a god's chariot or a fusion furnace, the deeper truth is the same. We are creatures who seek order, who need stories to walk through the darkness. And in telling those stories, we find not only knowledge but comfort, a gentle reassurance that the cosmos, however vast, can be spoken to, can be understood, can be sung into meaning. When you step back from the details of lithium, fusion and ancient stars, what begins to emerge is not only a scientific puzzle, but also a deeper story about humanity itself. For as long as we have walked the earth, we have been seekers of fire. The earliest humans struck stones together, coaxing sparks into flame, gathering around it for warmth, safety and companionship. Later we learned to shape fire into tools, into kilns, into engines. Fire became not only a necessity but a symbol of mastery, of our ability to bend nature toward our needs. And now, in laboratories where magnets hum and lasers flash, we attempt the boldest step yet, to summon the fire of the stars, to carry within our hands the very process that lights the sun. In that sense, the lithium problem is not just about missing numbers in a cosmological model. It is part of a larger arc, the arc of our attempt to place ourselves within the cosmos, to understand not only where the fire comes from, but why it matters that we can imagine it at all. Alchemists sought to transform matter, dreaming of gold and immortality. Physicists unlocked the atom, revealing both destructive power and creative potential. Engineers design reactors to hold plasma hotter than the sun. Each of these steps is part of the same trajectory, the restless search for light, for energy, for the secret at the heart of things. And yet, even as we master the flame, there are reminders that we do not fully command it. Lithium is one of those reminders. It is small, almost negligible in quantity, yet its absence unsettles us. It is as though, after building an elaborate lantern, we discover that one pane of glass is missing. The lantern still glows, still fulfills its purpose, but the gap draws the eye. You cannot help but notice the asymmetry, the absence that should not be there. In the same way, the lithium puzzle makes us aware of the limits of our knowledge, of the fact that even as we build fusion machines and chart galaxies, there are still details that escape us. This duality, our ambition and our humility, is what defines our cosmic place. On one hand, we are capable of extraordinary feats. We can split atoms, launch telescopes that see the edge of the observable universe, and simulate the evolution of galaxies with equations. On the other hand, we are humbled by absences, by silences, by small mismatches that refuse to go away. The cosmos does not allow us to grow too proud. Each answer brings new questions. Each discovery reveals another horizon. The lithium problem is humbling not because it threatens to undo all of cosmology, but because it reminds us that completeness is an illusion. There will always be gaps, missing panes, notes left unsung, and yet there is beauty in that. If the universe were perfectly understood, perfectly predictable, with no loose ends, perhaps it would feel smaller, colder, more mechanical. It is the missing details that keep us awake, that keep curiosity alive. The lantern with a missing pane lets out a sliver of light in an unexpected direction. The puzzle that does not fit keeps us searching for better tools. In this way, lithium is not only a scientific problem, but a symbol of the unfinished, of the ever-unfolding character of knowledge. Our cosmic place, then, is both privileged and precarious. We are stardust that has learned to look back at the stars to ask questions of the fire that made us. We are creatures of finite lifespans standing on a small planet, gazing at galaxies billions of light years away. We're apprentices at the hearth of the universe trying to copy its recipes, sometimes succeeding, often failing, but always learning. And in that apprenticeship, even the failures carry meaning. Alchemy failed to make gold from lead, but it seeded chemistry. Early theories of the sun's energy failed, but they led to fusion. Perhaps our attempts to explain lithium will fail too, and yet in the failure will lie the seeds of a deeper truth. To live in this cosmos is to live in between knowledge and mystery, between mastery and humility, between the light we have captured and the light we cannot yet explain. Lithium is a thread in that tapestry, small but significant, reminding us that our place is not at the centre, but within the whole, a participant rather than a master. We are not gods pulling the sun across the sky. We are not alchemists wielding philosopher's stones. We are not yet keepers of starfire, but we are seekers, and seeking is enough. So as you listen now, think of humanity's long pursuit of fire, from flint sparks in caves to magnetic coils in laboratories. Think of how each step carried both triumph and humility, both progress and reminder. Think of the lantern with its missing pane, glowing anyway, lighting the path but leaving a gap that draws your eye. That lantern is the universe. Its light is enough to guide us, but its incompleteness keeps us curious, keeps us from assuming we have seen everything. And in that gentle incompleteness, we find our true cosmic place, not as masters of all knowledge, but as wanderers carrying light, always searching for the missing piece, always humbled by the darkness that surrounds us. When people first told stories of the sun as a god, they were building a bridge. It may not have looked like one in stone or wood, but it functioned as such, a passage across the chasm of confusion, a way to step from the unknown into the known. To say the sun was Ra or Helios or Surya was to place a human shape upon the incomprehensible, to make the terrifying vastness into something approachable. That bridge was made of story and ritual, not of steel or equations, but it carried its travellers safely enough from one day to the next. It gave meaning to seasons, to harvests, to the endless return of light and darkness. It was a fragile bridge, but it was a bridge nonetheless. Science, too, is a bridge. It is built of other materials, measurements, models, and mathematics, but its purpose is the same. It allows us to cross from bewilderment to understanding, from scattered impressions to coherent order. It is not flawless, and it is not final. Like a bridge built over a restless river, it must be repaired and reinforced as new currents arise, but it carries us, and it widens the span we can traverse. Where myth once carried us across the gap of dawn and dusk, science now carries us across the gulfs of time and space. telling us not only that the sun rises, but how it shines, how long it will endure, and what atoms fuse in its heart. What is remarkable is that the two kinds of bridges are not opposed. They are layered, one upon the other, each extending the road. Myth gave us the first path, a narrow crossing of imagination. Science widened it, strengthening the beams, extending it further across the abyss. But the longing beneath both, the longing for coherence, for order, for a way to live with chaos has never changed. Whether we picture a god in a barge or protons fusing into helium, we are reaching for the same thing, a story that steadies us in the face of mystery. The lithium problem is, in its way, another bridge. It is a gap, yes, but also an invitation to build. Here is a place where our current understanding does not reach all the way across, where the boards of the bridge do not quite meet. We pause, we puzzle, we plan new extensions. Some may prove strong, others may collapse, but the attempt itself is part of the journey. Each unsolved problem is not a failure of science, but a reminder of its living nature. A finished bridge is no longer built. An unfinished one keeps workers engaged, keeps curiosity alive. The missing lithium is one such unfinished span, keeping us walking forward, hammer in hand. There is a temptation, when we hear that science is incomplete, to feel dismay, as if imperfection is defeat. But imperfection is the very reason the bridge is meaningful. A world entirely understood would be a closed book, a road already walked, a sky already mapped. Wonder would fade, questions would vanish, the thrill of discovery would be gone. It is the gaps that give us purpose, the silences that give us room to speak, the missing pieces that compel us to search. Lithium is a reminder that the universe is not a solved puzzle placed on a shelf, but an ongoing story being written in light and matter, a story we are privileged to read even as new chapters are drafted. Think of how myths once left questions unanswered. They told us the sun was a god, but they did not explain why its light warmed the soil, why shadows grew long in autumn, why eclipses darkened the day. Those gaps did not diminish the myths. They gave them mystery. Science has filled many of those gaps, yet it too leaves spaces blank. We know the sun fuses hydrogen, but we do not know why lithium is missing. We unmap the cosmic microwave background to exquisite precision, but we do not know what dark matter is. The bridges carry us far, but they never erase the abyss entirely. And perhaps that is how it should be. The bridge of curiosity is what links us across ages. A child looking at the stars today feels the same wonder as a shepherd thousands of years ago. The shepherd may have seen gods, the child may hear of galaxies, but both are standing on the same span, gazing across the same mystery, hearts equally stirred. What joins us to our ancestors is not the content of the story, but the act of storytelling itself, the act of asking, of reaching, of refusing to let the unknown remain untouched. In this sense, our cosmic place is not defined by what we know, but by our willingness to keep building. Each myth, each theory, each experiment is another plank in the bridge, extending us further across the dark. Some planks will rot, others will endure, but together they form a path. We do not need the bridge to reach the end of the universe. We need it to remind us that we're not standing still. We are moving, slowly, together, from chaos toward order, from silence toward song. So as you listen tonight, think of the bridges humanity has built, the mythic bridges of gods and chariots, the scientific bridges of equations and experiments, the unfinished bridges of puzzles like lithium. Each is part of the same journey. Each spans a little further, allowing us to walk a little deeper into the cosmos. And though none of them will ever reach all the way to the horizon, it is enough that they carry us forward, one step at a time, lit by curiosity held aloft by wonder. And perhaps, as you drift toward rest, you can imagine yourself standing on one of those bridges, high above the abyss of unknowing. Behind you stretch the stories of ancestors, ahead of you the equations of scientists, and beneath your feet the boards creak with questions still unanswered. The bridge does not end. It continues, plank by plank, built by those who came before and by those yet to come. You are part of that work, part of that crossing, part of the endless journey from chaos into meaning. And in that, there is a quiet beauty, the beauty of a bridge that is never finished, a bridge made not of certainty, but of curiosity. As our wandering draws to a close, it is worth pausing to see how far the path has carried us. We began with myths of the sun, the god in his golden chariot, the eye of the heavens, the radiant barge crossing the sky. We traced those stories into the work of alchemists, crouched over smoky furnaces, dreaming of gold and transformation. We followed them into the age of physics, where the atom revealed its hidden fires, where decay, fission and fusion became the true philosopher's stone. We stepped into the laboratories of the present, where coils and magnets hum with the attempt to bottle starfire, where lasers strike fuel pellets in hopes of sparking miniature suns. And through it all we carried a small, quiet puzzle. Lithium, the missing note in an otherwise harmonious song. The detail that reminds us the story is not yet finished. If you stand back, the pattern becomes clear. Humanity has always been restless before fire. From the flames of hearths to the fire of stars, we have been drawn to its warmth and unsettled by its mystery. Our myths gave it faces and names. Our experiments gave it equations and machines. Yet the deeper truth is that our relationship with fire, whether earthly or stellar, has always been a conversation with the unknown. Each generation asks, what sustains this flame? What is its source? How might we share in it? And each answer, however precise, is only temporary, for behind it waits another question. Lithium reminds us of that. It is not the dominant element, not the foundation of stars or planets, yet its absence speaks loudly. It tells us that even when we think we understand, the universe still withholds a secret. It is as though we have listened to a symphony that plays beautifully, each instrument in tune, except for one faint note that arrives off-key. That note does not ruin the song, but it lingers in the ear, reminding us that perfection is rare, that mystery persists even in the midst of clarity. And perhaps that is as it should be, for a world without mystery would be a smaller, quieter place. Think of all the bridges we have crossed in this journey. The mythic bridge of Ra and Helios, carrying us from darkness into dawn. The alchemical bridge of transmutation, flawed but hopeful, laying the groundwork for chemistry. The scientific bridge of fusion, spanning billions of years to explain the sun's endurance. The unfinished bridge of lithium, reminding us that there are still gaps to close. Each bridge is part of the same road, part of the same human impulse to reach across chaos toward order, to transform the incomprehensible into something we can carry. Our cosmic place is not at the centre of this story, but within it, as participants rather than spectators. We are made of the ashes of stars, forged in supernovae, sprinkled with the dust of collisions, nurtured by the light of a middle-aged sun. We are not outside the process we describe. We are inside it, woven of its very fabric. To study the stars is to study our own ancestry. To puzzle over lithium is to puzzle over ourselves, for the same atoms that defy prediction in stellar atmospheres flow also in our veins, hidden in our chemistry, part of our living bodies. And so the conclusion is not a final answer, but a gentle reminder. The universe is still becoming. Its story is not fixed, its mystery is not exhausted. Each day, new observations refine the picture. Each night, new questions open. To say we know the universe is not to say we have completed it, only that we have joined in its telling. Science, like myth, is a form of storytelling, one that is always unfinished, always growing, always alive, There is a quiet comfort in that thought. Imagine the universe as a lullaby still being written. The first verses were sung in hydrogen and helium in the dawn of stars. Later verses were added in the crash of supernovae, in the glitter of heavy elements, in the birth of planets and life. Our verses here now, written in the language of myths and models, fusion labs and lithium puzzles. And beyond us, new verses wait to be composed by generations yet to come, by stars yet to form, by galaxies yet to shine. As you drift towards sleep, think of the cosmos not as a solved riddle but as an unfolding song. Its melody is ancient, but its refrain is always new. It carries myths and equations together, weaving them into harmony. It contains both answers and silences, both knowledge and mystery. And in listening to it, in allowing it to wash over you, you take your place within it. A listener, a singer, a part of the lullaby still being written.